Hello everyone. Hello, thank you for everyone can come to our event today. I know it's been a long week and you guys are probably quite tired, but anyway, like thank you for everyone. Thank you. Before our research workshop, let me give you guys a quick introduction of our fund. So we Fenbushi were founded in 2015, and we have been one of the oldest institutional crypto investors from Asia. So actually, we are also one of the very early investors of Bitcoin. So we actually been into this data and storage space for a very long time. And actually, about like two years and a half ago, we even launched a Bitcoin eco fund with Protocol Labs together, and had invested about around like 10 projects directly through this Bitcoin eco fund.
This is a workshop on data and storage, and my talk is on data availability, which is kind of funny because this is like yeah, but I know this is like a general confusion in the space. Celestia have spent like months being like, no, DA is actually not storage, and now here I come and basically spreading misinformation, which is a great joy to me. Yeah, exactly.
Filecoin as a DA?
Yeah, exactly. Yeah, my talk is going to be on Filecoin as a DA layer.
Okay.
Oh, I don't think I need a charger, but now I'm going to show the world my PR. No, it's okay. It's a really nice PR. No, and I can actually use, I believe I can use this thing. Oh, really? I like it. I like it. Oh no. Sorry. My bad. Okay. So, at Repi Labs, we're building a layer 1 blockchain called Delta. Yeah. I'm not going to talk that much about Delta in this talk beyond, we're building a blockchain without consensus, which is, I know, that's exactly the reaction. Is it a blockchain? Very good question. Okay, so, cool. Topics of this talk. What is a blockchain? What are consensus protocols? Why do they go well together, or do they? Switching over to reliable broadcast, which is this primitive, which it's not a replacement for consensus, but maybe it can mitigate it. We'll talk about a simple case of consensusless blockchains, narwhal, and then we'll introduce Delta within this context. Finally, I promise, infinite scaling. I'm sure it's the first time you've ever heard anyone, any layer 1 blockchain proclaim infinite scaling. This time for real. Again, what's a blockchain? A blockchain is basically some STF. It takes in a state transition function, takes in some state, some block. What is a block? We'll get there. Output some new states, and that's like half the thing. The other half is you need some protocol to determine what this block is. And that's going to be the focus of this talk. So typically that is a consensus protocol. Consensus protocols are some way for some set of participants who may or may not know of each other. There are different protocols for either case. They certainly do not trust each other, and they want to agree on some value. I've just said here, some field element, you can kind of generalize this, but also we're working with computers, and we can kind of view anything as a field element, given a sufficiently big enough deal. Okay. Also baked into the definition of the consensus protocol is some number t. This is always some fraction of n. We typically care about Byzantine assumptions, so B of t. T is typically n thirds. And if this is the case, then a consensus protocol has a few different properties. We have agreement, all honest nodes agree on the same value. We have validity, which is if all nodes propose the same value, then that value is chosen. We have integrity, cool, and then finally, the protocol terminates. And termination is very important, right? Because, well, if we didn't have termination, you're invoking consensus time after time. Say you have some dishonest node, which just says, as a leader, I don't like you guys. Well, then you're never gonna make progress. That would be bad. Shout out DALI 3. So in a blockchain setting, we use consensus to agree on sub-ordered blocks. So we think of a block as like an ordered list of transactions. Again, I like to think of it in terms of the hash, but that's just because I like the idea of, we care about just the value. Doesn't matter. Okay, and also we focus on leader-based consensus in blockchain. I think all consensus protocols are leader-focused or leader-based. I know that in the literature generally, there are leaderless consensus protocols. I don't think it really works in blockchain. So assume the existence of a leader. Now, the leader is, and again, shout out DALI 3, who really seems to like this network topology. And, it's not representative of blockchain's IRL. They do not, whatever. Another sort of, I think, accidentally well-made point by DALI 3 here is that this thing, which is obviously the leader, is substantially bigger and better and more powerful than the other nodes. And in practice, you choose a new leader every time. So it's obviously not the case, but that emphasizes an issue because, well, this guy needs way more bandwidth than the others. The leader needs to send out the block. It consumes way more resources, and that becomes a bottleneck because, if the network is at half usage for most of the nodes, and let's say the consensus protocol or the network is such that the leader consumes double that of the replicas, well, then throughput is bounded at that point, which is bad. The other issue is it's a single point of failure in the case of BFT. I mean, for something like Bitcoin, obviously this is different because, you just have this hashing battle, completely different thing. We, again, care about BFT because they're efficient. In BFT, it's really expensive if the leader goes down or is malicious. You need to perform a view change. I think this is a reason why Tendermint or Comet BFT, as it now calls itself, why those blockchains have a max of 150 validators. I think it's n cubed cost or something. Is that right?
Yeah.
Nice. Okay, so, sorry. Leader-based consensus has some problems. Okay, what is a reliable broadcast? It's basically consensus without termination. It terminates if an honest node, broadcasts. It's not guaranteed to terminate otherwise. And this emphasizes again, we do not want to replace consensus with a reliable broadcast because they can literally halt the chain forever. The issue is, or the motivation rather, the idea is a different one. You obviously have a mempool, all the transactions pass through the mempool. Well, what if we could use a reliable broadcast for the mempool so as to ensure that all the nodes receive each transaction in the honest case? basically, going by this logic, what we would end up with would be every single validator has a copy of the same set of transactions. I emphasize set because the question here, do we need consensus? Unfortunately, yes. They have the same set, but there's no canonical ordering. What are you going to do? So you have DA, by the way, not consensus. I mean, people separate between the two, and this is kind of the reason. This is a great result. And I mean, this is one of the papers that I think has gone really under the radar. It's called, I want to say, it's called the consensus number of cryptocurrency or something like that. I strongly, one takeaway from this talk, check out this paper. The main result is, and they have like a theoretical construct called Astro, which is a Bitcoin-like blockchain, like very basic, no smart contracts, you can do payments, not much more. But it uses a reliable broadcast for its mempool and doesn't need consensus. It's an awesome result. And the idea is basically this. You have to think about like when do we need to order transactions and when do we not need to order transactions. And it's not like, and I mean, this is something that they are not the first or the last to have observed. Not all transactions need to be ordered relative to each other. So we'll go through what I claim to be the 4 only cases that we need to care about. First one is this. Alice sends Bob some coins. Charlie sends Daniela. I haven't said CS. Is Daria? Okay, it's Daria. In this case, what do we do with ordering? It doesn't matter, right? From the system's point of view, it does not matter in which order these things take place. Next example, both Alice and Charlie send Bob some coins. What do we do about ordering here? Doesn't matter, right? The end state is the same. Okay, next one is a bit more interesting. Alice has 3 coins. She wants to send 2 coins to each of Bob and Charlie. Well, this could be an issue, right? We have no sense of ordering in the system. Well, some honest nodes will think, okay, Alice sent Bob 2 coins, but then she didn't have enough to send Charlie coins. Cool, that transaction didn't go through. Other, equally honest and valid nodes would think the other way around. We have a problem. So the solution is essentially nonces in this case. Nonces are these, you have some number, some natural number tied to positive integer, sorry. Tied to each transaction, it's tied to your account, it needs to go up by 1 for each outgoing transaction. Alice needs to order these to herself, so she needs to say, yeah, I pay Charlie first and then Bob, or the other way around. And then this one, the most interesting one of them all. So, okay, Bob has 0 coins. He is broke. He wants to buy a hot dog from Daria, which costs 4 coins. But luckily for him, Alice is sending him 6 coins. Okay, so what about ordering here? Again, it obviously does matter. We cannot have this one go through before this one. So again, Bob ordered the transaction. So the essentially 2 rules that exist here is each account needs to order all outgoing transactions with respect to each other and with respect to a subset of the incoming transactions. And the thing is, because we have reliable broadcasts, the availability of all of these transactions, assuming honest behavior, is available. We have data availability. So we don't need like this external step of going through consensus to reach like a consistent end state of the system. Again, awesome paper, awesome work. Check it out. Called the Astro, paper called Consensus Number of Cryptocurrency. Cool. So narwhal is, and this might be just me kind of interpreting history. I think it is valid. Basically, these Facebook people came out with fast pay, similar to the previous paper. I think the previous paper came out first. I might be wrong. Sorry if so. Basically, fast pay is it's very similar, and then they came out with narwhal, and I think the following thing went through their heads. Okay, this is very cool. We can do this payments thing without consensus. What about like normal, smart contract blockchains? It seems so unnecessary that in those cases, so many transactions unnecessarily have to go through consensus when we could just have a better mempool. Narwhal is a better mempool. So Narwhal is reliable broadcast as a mempool. It can be used in any blockchain, Aptos and Sui, I think. At least Sui uses it now. I think Aptos is integrating it as well. Yeah? All right, there you go. Yeah, so basically, same sort of thing. I believe in Move, they have the concept of owned objects and shared objects. Owned objects are like, tokeny things, NFTs, your USDC, whatever. If you're just sending someone this stuff, they just have to go through Narwhal as a mempool, no consensus whatsoever. And then the nice thing for Narwhal is, the things that do need consensus, which is when you interact with a smart contract, for example, like an AMM or something. Two people interacting with an AMM, how is that going to be ordered? It's no longer so simple. In those cases, you just can plug in a consensus protocol on top. So it's basically, you only have consensus for transactions that touch shared objects. Nice. Now, the Narwhal thing was honestly a bit of a detour in terms of like the linear development here, because Delta is in this sense much more similar to the work by Guarawi et al. But I wanted for historical completeness and whatnot to include it. Okay, so commutativity, for those who do not know, it's think of, you have two actions, you want to change some state. Basically, the order in which you apply them doesn't matter. That's what commutativity means. Commutative ordering means we don't care about the order. So, at a very high level, we separate DA, and I should say we include settlement in that, from execution. However, unlike something like Celestia or Ethereum, where all of these are, sort of individual mix and match components, we have an integrated system, and they have a global state. Okay? So, what you guys would maybe call rollups, we call execution charts. They are really qualitatively different in the sense that, they don't have their own, fully owned state. They sort of rule over a subset of the global state, and I'll try to explain how. Also, we call what you would call a sequencer, we call an executor. It does both. We just think execution is kind of, more important than sequencing, although both are important. And arguably this talk is about sequencing is important. So the executor essentially does, and this is where it's very analogous to the work by Guarawi and co-authors, the executor orders all of the spending transactions within of accounts within that shard. So that is to say, sort of all outgoing transactions, instead of having those accounts have to order them themselves, the executor does it for them. And this can now include things like smart contracts within that shard and all of that. So it's essentially, from this point of view, consensuslessness, just replacing the need for each individual account to do this by having these big guys doing it for the entire shard. And yeah, this gives us a partial order, right? Because within each shard, the order is determined by the executor, and then between them we have commutativity. Because we're essentially, partitioning the state. I mean, this is like the definition of sharding, right? Is you're partitioning something into different sets, which make up the whole and have zero intersection, empty intersection, sorry. Okay. Yeah. Yes, this is a great illustration, I know. The next one hopefully will make it clear why I included this absolutely horrendous looking thing. The idea is basically you have these distinct accounts which are separate from each other. They do all their ordering, they send, here it's just fun and DA and no ordering, no consensus, no nothing. This is actually, yeah, whatever. But now you'll see why I have this ugly thing. So we clean it up to this, where the order is now not done by, each individual guy here, but rather by these guys. And you could think of each execution shard as like roughly analogous to rollup in the sense. You can have smart contracts, you can have all sorts of things for cross shard interactions. We do have that, but that is not going to be a topic of this talk. Slightly more involved. Although honestly, this paper by Guarawi et al., I know I keep going on about it, it kind of offers a solution to the cross shard thing here as well. I don't think I have the time to go into it though. Oh, did I want to say anything else? I don't know. Maybe one other topic I want to mention. So just to say explicitly what goes on here, there is no consensus here. These guys are just sending down their data, and it's not ordered, okay? It's not ordered. They only send it and essentially stream it throughout the validator set. This is different. This is new. So we can think of this as essentially streaming. You mitigate the overhead of having, this is like the most literal bottleneck, by the way, and we'll get to this with the infinite scaling. If you have sequential dependencies and the need for a total order, I mean, that's like the definition of a bottleneck. You need to squeeze all the data through this one thing called consensus. Terrible. We're done with that. Not quite done. Last topic, infinite scaling. Okay, so we have this thing that looks like this. Obviously, execution can be scaled to whatever degree possible or necessary because you just add new shards. And something you don't know, but which is the case, you can permissionlessly open up new execution shards, no problem at all. Execution is never going to be a bottleneck. However, the bottleneck that you do reach is these guys, they can only send so much data around, At some point, you reach that limit. What are you going to do? By the way, this is not something that's specific to our chain, right? Like, this is really like the ultimate, the final boss of blockchains is the internet. Okay, what do we do in that case? We reach the limit of what these poor guys can, send through the network. What do? We do this. So, because we don't have the overhead of consensus, you don't have the need for this sequential dependency. You don't have the need to add relations between any of the things that come in. So what we do, and by the way, if you thought this was going to happen without extra hardware, I'm sorry. You need hardware. But this is also like obvious, right? Like if you want to squeeze like 10 gigabits of data through some network, well, guess what? Each validator needs to have that internet connection. Like, sorry. Okay, so basically what you see here is each validator runs like two computers next to each other with their own internet connection and all that. And you have 2x the throughput. And you guys are like, that sucks because you shouldn't be like, that sucks. That is really cool. But, you know, at the off chance, that is, you're demanding more hardware, hardware decentralization. First of all, okay, like you do need to make some trade-offs. In the grand scheme of things, if you want a network with really high throughput, well, again, they need the internet connection. Secondly, though, we should assume that like the profits or the profitability of running a validator is like roughly proportional to the amount of data that it deals with. So I would assume that they would want to add another computer because it means they're going to make more money. Okay, that's enough of that rant. Cool. Oh, another thing that I want to mention, by the way, not tied to this, but I'm trying to nerd snipe. What do we do with bridging here, right? They're usually in safe bridges, you need consensus proofs, right? Here we have no consensus. Does that mean that bridging is suddenly trivially easy, or does it mean that it's suddenly impossible? If you're interested in that question, you know, yeah.
Can you hear me? Okay. Well, thank you so much for introducing this concept. I remember back to like 2020, I was super obsessed on finding the next Ethereum or Ethereum killer. I came across a lot of like protocol consensus. Some of them like similar to hash graph. Some of them are similar to what you just described, like reliable Byzantine broadcast. But I have one question I like really wanna ask. Like, seems like all this kind of system relies on one property, which is you always need to know the big N in the system, like how many validators, the total number of validators. Because one of the prerequisites of like Byzantine like broadcast like algorithm is like you have to reach message to every single validators, right? So how you like the beauty of the Ethereum and the Bitcoin is you can hop on, hop off. Like I can run a validator and secondly I can just drop it. Like how you make sure in a scalable system, like without consensus, if we don't know what's the total number of N, how we can still have like how this algorithm can still work.
Yeah, it's trade-offs all the way down, right? And I said this quite early on when I said we focus on BFT systems, so not like Bitcoin and Ethereum. I do agree with you. So, you know, just explicitly how these things work, like reliable broadcast, you have some certificate based on the quorum. Typically that will be based on something like stake or whatever you want to have, right? So this is of course true. You do need to know of the other participants in the system. I agree, would have been better if it weren't the case, but c'est la vie.
Okay, cool. Seems like in this case, it's probably more useful for like enterprise scenario, right? Like, well, like maybe within Amazon, they have fixed number of servers. They want to validate their data and their information is on a blockchain, secure. Probably in that case, more useful.
I think you're underselling it. I mean, I get what you mean, but like most modern consensus is like this, right? Like BFT consensus, again, Comet BFT or Solana or most anything that isn't Bitcoin or Ethereum. Maybe not Cardano. I guess Cardano, but okay, yeah, whatever. I get your point. I think it generalizes far beyond just enterprises. Yeah. For example, Celestia is also, right, like Comet BFT.
Howdy. Yeah, thanks for the really cool talk. Definitely interested in reading the consensus paper. I'm curious how this changes the typical threat landscape through protocols, especially since you're talking about, well, what, Byzantine fault tolerance, you need to be resilient to malicious nodes. Things like Celestia or other DAs, you say, well, we don't care about the execution, so just, if it doesn't make sense, ignore the message. How has that changed in what you presented?
Yeah, so there are different kinds of nodes in our system. Maybe I should just briefly, we have these things called executors. They execute and then we use snarks, to prove the validity of execution. So they definitely, they can try to pull some tomfoolery, but I mean, unless they can break the snark, they will be called out. These guys, the thing is, if you just have reliable broadcast, which is a strictly weaker primitive than consensus, you would assume that there are strictly fewer ways you can attack the system. So my kind of informal heuristic assumption is that these systems will end up being strictly safer and, less prone to attacks. But it's just based on that heuristic, right? Weaker primitive, fewer attack surfaces, or less attack surface. What do you think?
So as a follow-up question then, if you have a weaker primitive, like we have a stronger primitive for a reason, so what are the things that we can throw away in the weaker primitive that allows us to be more efficient?
Yeah, so as I said, reliable broadcast is really not to replace consensus, right? It's not like we take out consensus and put in reliable broadcast, but rather you have the mempool, which everyone has anyways. You have it work this way, and then the only thing that consensus can really provide you with is ordering. So what do you lose? Well, you lose ordering. And for most blockchains, that's prohibitive, right? This isn't something that most blockchains can adopt. Ethereum cannot tomorrow say, oh yeah, that was a cool talk. Let's do it.
What does the finality look like?
Should be pretty fast, no?
As in like these, because there is no consensus here. So
Yeah, so I think this is actually a really good question and something that we need to explore more, because reliable broadcast is guaranteed to terminate for honest actors. So that means if you're honest, it's guaranteed to terminate, but it doesn't say anything about when. In practice, we use these, if you use these certificates, you know that 2/3 of stake you basically have the data, so it's easy to pull it. Yeah.
Because I'm trying to understand, at what point am I? Because you could have multiple different parties that could be competing for different ordering. For example, and that in that case, I'm not sure what exactly would be the finality condition for determining the right ordering.
No, we wouldn't have something like that, because there is no ordering whatsoever. So you only have all these nodes which just receive the copies of the transaction, similar to a mempool, right? So we're strictly removing the overhead of having consensus on top of the mempool. Does that make sense?
Okay, I see.
So the finality, latency, should be strictly lower. Again, we haven't implemented this yet. Cannot really give you any numbers, but fingers crossed.
Sorry, I'm still confused by the execution sharding. So, if you have very complicated smart contract dependencies, how does this sharding actually works? And also, I think in the talk you mentioned, for example, all spend transaction is going to be put in that shard. I'm confused isn't all transactions a spend transaction?
Yeah, so outgoing transactions.
Yeah.
So
So maybe just the real question is how does can you give us some example? How does the sharding actually work? The life cycle.
Yeah, it's similar to a rollup in some senses, but I guess the main case that is different is, let's say you're on shard 1 and I'm on shard 2. Mm-hmm. Here you can just send me some tokens, but you just tell that to your executor. You cannot tell that to my executor, right? So.
But how can I make sure that if someone send it to you and send transaction to you and some other people send transaction to me, how do we know that the transactions will not have dependency?
What do you mean?
For example, my transaction is interacting with one particular DApp and your transaction is also interacting with another DApp. They send it to you as a shard executor and also one sends it to me as another shard executor.
Yeah, well, all of these are associated to a shard, so this gets checked explicitly. This is not just hope and pray. It's being checked explicitly and needs to be proven as well by the executors that this holds. Now,
but doesn't that checking require some communication between you and me and that kind of?
You mean as executors or as?
Yeah, executors.
No, let's say you're a user, in your account says shard 1, and I'm an executor, then I just need to prove that it says shard 1 in your account.
Okay, well, maybe let's talk off.
All right, listen. Yeah.
Yeah. You mentioned that the executor is a large node. It seems like a pretty important node of the network. Who's running those?
Yeah, I mean, it's analogous to something like a rollup sequencer. Well, that depends, right? Because some rollups now are thinking, we're going to split up the sequencer from the prover from the executing client. It is a really beefy node. One advantage of the network, and now I'm really going beyond the consensus thing, but they can be centralized without harming the network because you have this global state, so you can basically just switch between these. And by the way, that induces more complexity, which I do not want to go into now. Basically, they can be beefy computers without harming the censorship properties of the system. You obviously have snarks to prevent invalid computation, so no invalid state transitions can take place. But additionally, you do have censorship resistance. But yes, they're going to be beefy as hell.
I wonder if you can dynamically change the partition. Because if you can do that, then if my state on the yellow partition, if I have to do some interaction with the one in the red partition, I don't have to talk to the executor, right?
I don't think I understood the question. No, you cannot. So that has to explicitly be done. Like you would change the partition basically via the transaction that says, "Hey, I'm now in this shard, but I want to jump here," and then you do that. Did I understand your question correctly?
Yeah, I think my question is like more on can you change the partition later on?
Yeah, but again, the partition only can be done explicitly. This is like sort of analogous in that sense to bridging between blockchains, right? Like it will not just happen on its own. It needs to get, invoked on purpose by the participants.
It's interesting that we are in all capital scale byzantines, because these things are desperate to talk about. My question is, does this system work under asynchronous systems like IoT or another things?
Yeah, I think they are inherently async, right?
Yeah.
So I would say yes, but no, don't take that as a sure answer. Not sure.
You want this?
No,
So, you turned it off. You can take this. Okay.
So thank you, Ole, for his presentation. So next, welcome, Malcolm.
Awesome. For staying, everyone. My name is John Victor. I'm an ecosystem lead at Protocol Labs. So I work on IPFS and altcoin things. So today I want to talk a little bit about how we go from data to storage. So before talking about Filecoin, I want to talk a little bit about IPFS. For those unfamiliar, maybe the pithy two-liner is IPFS is about content addressing and Filecoin is about markets.
Sorry. Yeah, so maybe to preface, why do we care about content addressing? What does that enable? Maybe start with what content addressing is. Typically, when we think about like how we reference data on the web, we're doing it based on locations. We're saying, go to this specific server, go to some path inside of that server. This is the data that I'm referencing. And of course, that's like not a very specific way of referencing data. If we were talking about humans that way, it would be quite ridiculous to say, I'm the human that lives at 300 Graham Avenue or works at 15 Little West 12th Street. You'd have no way of knowing that that is the same person. Instead, when we talk about content addressing, we're saying, what if we could build the web to reference pieces of data based on fingerprints, or in this case, content hashes of the data itself? And this is really the thing that IPFS is focused on. In the analogy I had with a human, instead of talking about where that human lives or where that human works, we're talking about properties of the human. It could be their eye color, their like genetic sequence, whatever, but something so specific that we know that it's that human, regardless of where they are. So when we build applications with content addressing as a core primitive, what does that enable? Well, thing number one is it means that we can build applications that run local first. Without having to go to some central server, we can have applications that just work with the data that might be sitting locally on the device. This also implicitly means that we can build applications that run at the far edge. As Boris and the Fission team will talk later on, this can be really powerful when we have applications where you may be in like bandwidth constrained environments. Maybe it's an airplane, maybe it's in some part of the world that doesn't have internet access, maybe it's in space.
These are all places where you would want to be able to do things with data without having to go out to some third-party server to go grab it. Third, it also means that we can make use of hardware wherever that hardware is. It could be a user's device as the new MacBooks get more and more powerful. It could be an on-prem server. So if you are a business that has your own server, it could even be a third-party cloud. Across all of these different hardware platforms, we're still using the same content hash, which means that our application is no longer tied to one specific server, but rather the data structure itself. So why does this matter? Well, one is it gives you better security. The data is verifiable, which means that you can actually start building applications where trust doesn't emanate from some arbitrary server or who owns that server, but rather from the data itself. Regardless of who serves you the data, you can always verify that the data that you asked for is the data that you got. This also means better resilience. When you have maybe one server goes offline, so long as you can ask someone for that piece of data that you're looking for and you get the right bytes back, you can still have your application run. So this gives you better resilience. And third, and maybe this is a little bit more like future looking, but this does ride on broader trends that we're looking at in terms of hardware improvements, in terms of data generation, in terms of the requirements for verifiability as computers and AI do more. Now, this is all sort of like the precursors. I didn't want to go too much into IPFS. Other people will talk about it later today. This may lead to a question of what does Filecoin do in this vision? And really, if you sort of bought that very short and maybe too fast pitch on IPFS, the thing Filecoin is really trying to say is if we believe this world that content addressing really is the future and that there are valuable reasons why we want to build all applications, irrespective of how bought into Web3 you are with content addressing, the bet that Filecoin makes is that there's two divergent paths of the internet. One is we use content addressing everywhere, but we still just use the hyperscalers whenever you don't use like compute on a local device. The other is that we can build markets that say, for the services that I go to the cloud for, can I build an open market where I can just go to whichever computer can do this service the best to provision that offering? So if we were to take a 3,000-foot view of Filecoin, and for those of you who have not checked in since the 2017 white paper, this may look kind of different, but this is what we're building. Filecoin is building open services for data to serve web scale applications. And this is all shared or anchored into the same shared rails. I'll come back to this diagram, like keep it in your brain, but I'll keep going through it so we can like tick through where things are on each of these sort of like little modules. This is not to say that we have fully built all of this and it's 100% perfect. This is like the orienting vision of like, what are the core components that we need that will continue to mature that get us to this end state of like, how do we build open markets for the web? So go to market. What is Filecoin's master plan? Well, we've broken it down into three main stages. The first is to attract scalable data storage. This is really just talking about how do you build out your supply side. Attract exabytes in capacity, things where you can start actually competing against Web 2 at scale. Build out a network that can store large amounts of data. Part two is to start filling that capacity. Start bringing more and more data into that network and leverage the cheap storage because you have massive supply in order to actually bring a competitive offering to market. This also implies needing to shave down the friction in onboarding pathways because fundamentally, when you're building in these open markets as your backend, there's a lot of new problems that you have to introduce, and maybe we'll talk about them at the end. The third is bringing out services that make that data useful. Once you've built out your internet scale hardware, once you've added data on top, you want to start adding more and more services that can compound the utility of the data that's sitting on those hard drives. This includes things like compute. So now that I have the data sitting on a hard drive, how do I run transformations if people want to run compute jobs? How do I make it more accessible? How do I serve the wide range of applications that have different retrieval properties to them? How do I start programming services around them? And this is where like FBM and IPC come in. So now I'm going to go quickly through each of these different buckets to sort of like say, where are we today and how are these things progressing? And then we'll have time at the end to sort of talk about, whatever questions folks have. So part one of that vision was scalable data storage, which was attracting all of this exabyte scale hardware. So how are we doing on that? So today there's about 3,400 storage provider IDs on the network. You can see this little heat map of where are these providers today. This is not perfect coverage. As you can see, we have a lot of representation in Asia, some in Australia, a lot in Europe, a lot in North America, but still some noticeable gaps in South America and in Africa. But in totality, we have about 10 exabytes of storage capacity. For those unfamiliar, it goes like gigabyte, terabyte, petabyte, exabyte. So we're large is, I guess, one takeaway from the slide. We're in 40 countries, but hopefully continuing to grow. especially as the market picks back up, we hope to see more and more storage providers start standing up operations in these areas where there's gaps. Part 2 is massive data onboarding. You can see at the bottom this chart, which shows since February of 2021, how data onboarding in the Filecoin network has grown. We've gone from like under a petabyte to about, that's like 1 exabyte and some change, almost 2, of data onboarded into the network. And you can see that it's coming from all over. Some of these are Web3 users. They're folks like Gala Games, OpenSea, a bunch of NFT projects, but also some traditional players as well. You have folks like Berkeley, who's storing particle physics data. You have CERN, who is also storing particle physics data. You have New York, who's storing open data from their open data project, the Internet Archive, and more. For a lot of these institutions, the core driving property here is not because, I mean, for some of them, it's like testing the waters, see what the future of the cloud could look like. But a lot of this is also just, I have a lot of data, this is a cheaper offering, this makes sense. This slide is wrong. The third part here is like, how do we enable web scale applications? And I'm gonna touch on from storage into retrieval, compute, the FVM, and interplanetary consensus. So moving to retrieval. So when we talk about retrieval markets, in 2017, if you go back to the white paper, there was a number of sections and people really focused on the storage part, but there was a call out actually for retrieval markets and this vision of building basically like the other half of what you need to do the reads and the writes. When we talk about retrieval markets, what we're really pushing for is how do we build distributed CDNs? And so why do we think retrieval markets are a good idea? Well, content addressing, as I mentioned before, means that we can have verifiable data that is served over untrusted servers. When I can verify the data itself based on what the bytes are that I get, I actually don't care which server gave me the data because I don't have to worry about you sending me malicious things. 2, crypto incentives are quite good at building up and aggregating resources. When we talk about a CDN, the thing that really matters is getting as close to users as possible. What you want is points of presence that are physically as close as possible because then the latency for delivering that content can be lower. So if you combine these things together, you get a DCDN. If you can take incentives, you can have a permissionless network of providers stand up, hopefully getting as close to the users as possible. We can then serve these like verifiable pieces of data to the users themselves. The users can trust that the thing that they got is the thing that they wanted, and you now have the magic of using the incentives of Web3 to build a CDN that might be larger than any of the ones that, or hopefully at the end scale, is larger than anything that we have from Web2. Where we are today, this is actually just a heat map of Saturn. So Hannah from the Saturn team is here, so hopefully she'll be talking a little bit about some of this stuff too. Today, there's over 2,200 points of presence around the world, a median time to first byte of around 66 milliseconds. You can see some of these other stats. But I want to like highlight one important piece, which is Saturn is just one of the retrieval market teams that's building in the Filecoin ecosystem. So I think what's really cool about Web3 is like when you have a lot of people working on the same shared interfaces, you have many bites at the apple. And so what we see is like Saturn is doing amazing work and sprinting quite far ahead, but we also have the opportunity to have experimentation on what are the other ways to fill these gaps and continue to build out to cover the rest of the world. Compute over data. So compute over data may seem kind of weird. Why should this be paired with the storage and the retrieval side? And a lot of this comes back to this idea of like the interplanetary principle, which is something that Juan, who founded Protocol Labs, talks about quite often, which is really trying to minimize these round trips and do operations wherever like locally you can. And the reason for this is kind of simple, and you can sort of motivate it by just thinking about data having gravity. If you have a petabyte of data, it's actually quite expensive to move that around. Like if you just think of what would it take to move it from one data center to another, you're introducing both latency and cost. And so instead, you would rather move the compute to wherever the data is. Because if you have a compute job, you can send whatever request you have down to the data itself, run the process, get the result, and either ship the result or store it locally there for someone else to come and compute on later. When we think about compute, though, of course, there's different trade-offs that you're going to have to make. And so this little diagram is what Juan calls Juan's triangle. But you can sort of think of there being some contradictory properties that are sort of at play. And depending on application, there's different things you may want to optimize for. So if you want to do privacy, you might want something like fully homomorphic encryption, which is something that like Sama, as an example, is working on. This gives you privacy. You don't have to reveal your data to the person who's doing the compute. The downside is you're adding all these extra cryptographic cycles. on the other bottom left triangle, maybe you care about verifiability. You'll want something like recursive snark, so you can verify the compute all the way through. Teams like Lurk are working on things like that. Of course, again, you're adding in these additional cryptographic cycles. And so for both privacy and verifiability, they may satisfy a condition, but if performance is what you're looking for, you may want to opt for something closer for like Bacalhau, which is doing distributed compute in a more optimistic way. And so the goal with what we're building as an ecosystem is not to say like there's a single compute that will rule them all, but more observing that there are inherent trade-offs that you'll have to make. And ideally, what we can do is build interfaces that allow us to basically say, for the application, or even the subpart of an application, you can make the appropriate trade-off that you need to for whatever thing that you're building and compose with everything else in the ecosystem. I'll also note the way that the storage providers are built. I don't know if folks are aware, but Filecoin is probably the largest in production use of snarks as it is today. All of them have like a large amount of GPUs and CPUs. This also makes them a prime target for actually deploying these compute jobs. As are, hopefully, when Saturn goes live, the Saturn nodes as well. It's interesting, as a brief aside, there's a new team in the Solana ecosystem, IONET, who's like building this large ML network. And I think actually they're sourcing their GPUs from 3 different networks, their own, Render, and Filecoin. And ironically, Filecoin is the largest in terms of like the GPU sources that they have. Okay, so I have very quickly whipped through all of the things that are happening off-chain. These are all the services that from the Filecoin ecosystem, we want to be invocable, things that you can like call out to and have different services in the network perform. So how do we actually do that? This is where the FVM comes in. So the FVM itself is semi-complicated. It's a WASM-based VM, but it's designed as a hypervisor. And the idea with the FVM is that you really want to bring programmability around Filecoin state. And so this means a number of things. The 2 ways I describe it is it gives you the ability to program your data. So if you want to do things like invoke a storage request and say like, someone please store this piece of data, that's something you can trigger from the FVM. It also means that you can do things like, in the future, invoke a compute request. So say like, someone who is holding on to this piece of data, please perform this computation and then return those, store the results, and then post some proof on chain, and then release some funds. So those are things that you can do with the FVM. It also gives the ability to program payment around those services. And so if you wanted to pair those 2 things together, you can think of things like building a perpetual storage protocol as really saying, how do I build a data endowment where I use DeFi to generate yield and make sure that the yield I'm generating is larger than the ongoing expense of my endowment? But it also gives you the programmability to say, if one of my 5 copies of this piece of data falls off the network, I want to set a bounty that the next person who stores a copy gets to claim a little like prize. This also gives you flexibility to start doing more and more sophisticated things. It allows for saying, how do I have multi-currency payments? So if I want to have a compute network that pays in its own like coin, you can happily do that and then use an AMM to swap to whatever currency that storage provider wants. And of course, like storage options or things that people have talked about. Actually, the biggest thing happening on Filecoin DeFi right now are these collateral markets where storage providers are using these lending markets to effectively acquire more collateral to grow their businesses faster. And it also leads to some interesting use cases for things like basically like tokenizing cash streams of these various businesses that anchor onto Filecoin's rails. The last sort of piece here is interplanetary consensus, which is really about how do we scale sort of like the deployment of all of these things. IPC really is focused on that top right, which is solving for basically a bunch of what would seem like contradictory properties. So if you want something that is internet scale, so you have like trillions of transactions per second, and this is not for a single network, but across a network or a hierarchy of networks, like that is at contradiction with something that has like maybe like global censorship resistance. If you want super fast local finality, that may also be in contradiction for something that has secure global finality. If you're worried about like nation state attackers. And like the reason I put this up is it's more starting from in the top right for what are the requirements that you want, but not saying that one network has to solve all of these problems. It's just saying that across like a hierarchy of networks, you need different regions of these networks to solve these problems. So at the base layer, so like at the root chain of IPC, you can have, in this case, this is the Filecoin network, you can have the thing that we canonically think of from blockchains, which is like global censorship resistance, like all the good stuff, and you can hold your value and do all that stuff there. But you can have a pathway to get to less secure regions of the network where you can make the explicit trade-offs and say, hey, I don't need global censorship resistant whatever, but I can build a local CDN region, which allows me to cache data and just send it there. And like the analogy others have used is like, one way that you might conceive how this would work is like, you could have a region of a CDN that operates even in like one specific geography, like AWS East, and you don't have to hold all your value there. You just have to inject small amounts of money and just spend it down. But then you have the ability to do things like have super fast delivery of content that can operate at like the performance that you need to compete with like Cloudflare. Some of the things that makes IPC kind of interesting is it's on-demand horizontal scaling. Today it's using sidechains, but the way that it's being designed, it could be rollups in the future that's like on the roadmap. You can swap out the consensus mechanism, so it doesn't have to use the stuff that Filecoin uses in space layer. You could use things like Tendermint. You could in the future theoretically use like Avalanche or Polkadot. There's more things that you could sort of like slap in there. And it also comes with this like native messaging property, so you can send messages up and down the hierarchy. This also means because you can go up and down the hierarchy, you can go across the hierarchy as well. But that's maybe a deeper talk. But yeah, putting all this together, so Filecoin's master plan really is around like, literally how do we acquire all the hardware? How do we make that hardware useful? And then literally like, what are the raw pieces that we need to do that? We think of them in these three major buckets of like storage, retrievable, compute. These are all in various degrees of like completeness. But the important piece is like, once you have these three different types of services and have the composability through things like the FVM and scalability through IPC, you can actually start building really complex applications. So there's some really good papers that are out there. If you go to ipc.space, you can see a really good one from the IPC team about what would this look like if you were building a fully on-chain game that really relies on all these different properties. But yeah, this is sort of like our vision for how do you actually build out to like web scale applications running on Web3 Rails. Yeah, thanks.
Thank you, Jonathan, for the speech. So, anyone have questions? Let me ask the first question. So, like for the services being built, like storage, machine learning, they all need to incentivize like to do the job, right? So, like from protocol point of view, like, are you guys want them to each have their like own tokens, or about like in the end, like so those because of the price of token are different in some way, and those like service providers might be incentivized to do the work that have like most rewards, so that the whole network of the service are somehow impacted.
Yeah, I mean, so I don't think we are trying to specify like, oh, one token to rule them all. Like I would say, think of the role of Filecoin closer to the role of Ethereum, where it's like, you're using Filecoin to pay for gas, people can have whatever ERC20s they want, they could also pay in wrapped fill. I also think once you have DeFi, it's a little bit less important because the miner will just convert to whatever currency they want to hold in the end. I do think it's interesting more for things like subnets, where it's like, if you're a compute network, having the ability to have your own gas token for that subnet. So as you distribute load to potentially just small clusters of SPs, like that might be actually a better use case for your currency rather than like just using it as like a medium of exchange. But yeah, so I think like Filecoin is trying to build more flexibility, not necessarily like lock people into a specific mode. I imagine what we will see is things like, so I mentioned this idea of like data having gravity. I think one thing that's probably underweighted inside of crypto is, at least for the people who are focused on DePIN, that probably means that there's going to be bidding wars for GPUs. More specifically, like if you were to compare a GPU that's sitting in Buenos Aires versus like a hard drive that's in Scotland, like that GPU to quote a compute job would have to like also price the the bandwidth that it would take to like grab the data off this hard drive, move it down, do the compute and send it back. Like that's going to inherently be more expensive than the GPU that's sitting next to the hard drive. And so what's going to probably happen is like the GPUs that are probably the most valuable are sitting next to the most amount of data because they will have like a structural advantage of not having to pay this like retrieval and like distribution cost. And so I think you're going to see like a consolidation of hardware. Again, this is my perspective, but also very, very biased. I think you're going to see like a consolidation where all of these DePIN networks are going to like layer on top of each other purely for cost efficiency reasons, which is partially why things like IPC are kind of interesting because it gives folks an opportunity to build, whether they want to be a roll-up on Filecoin or be a side chain to Filecoin, an opportunity to be more composable with the ecosystem.
Yes, good, thank you.
Yeah.
thanks for an awesome overview. I've never seen like everything put together so succinctly, especially with everything that Filecoin IPFS has. One, I really like the idea, like you said, instead of based addressing like topology or whatever, where it sits the content addressing, especially with what you just said about like the consolidation of hardware. If you have a network where everything is addressed by content and it's kind of like location agnostic, how can you ensure that the GPUs are next to whatever you need? Or especially in your thing with like a DCDN is a CDN, crypto and content addressing all in one. How do you ensure, because a big thing about CDN, right, is about putting low latencies to users. So how do you guarantee that?
Yeah, so I mean, there's various ways that people have discussed this. I think like actually the core insight is going to come from things like these consensus hierarchies. So there's a great talk if you go to YouTube and type in IPC applications, one has on like how he thinks about these things, and I'm totally going to just quote from there. But I think like one of the ideas is building out regions as like a concept. So one of the things that he's sort of talked about is like you could have a subnet that is just of a specific region, and then you can have subnets inside of that. So like that might be like a region, and then go even further down, even to like the city level. And like you basically want to be able to like index into these different subnets to like place content there. And so I think there is some properties of like, okay, so how do I know that this subnet maps to like the Atlanta region or something? I can imagine a few ways that you get there, where you can take a hybrid of off-chain and on-chain information. There's a sort of example here. Like a lot of the storage providers in Filecoin's network are also, I mean, they are all businesses. And so like Ernst & Young is going through and working with a number of them to do like SOC 2 certifications. Now that's never something that you're gonna like cryptographically verify that like you are all fully secure or whatever, but you could tie that with a verifiable credential to say like, hey, this storage provider ID, which is like an ID that they have to get through mining over this period of time, it's not easily replaceable, that is tied to this attestation, which is from a known set of entities, whether it's Ernst & Young, KPMG, whoever, like that shows that they have this thing. And so you can think of using like those identifiers tied to like the network primitives. So like the network primitive of like, what is a storage provider ID, which is like unchanging, to something that is like a verifiable assertion from a number of known parties, and you can choose how many you need to be confident. But that could just then give you the delegation of like, oh, this thing is in XYZ region. For some of the like the lower subnets, you may also add like latency parameters where it's like you just jack up how fast you need these things to run, where it wouldn't be possible to be in a location that's outside, just because the time to finality would be too fast and the speed of light wouldn't let you get there. So like my answer is probably like it's a mixture of things. Both like merging on-chain and off-chain information, but then also if you set network parameters anchored against some of that, it would be impossible to participate in consensus if you were like in a different geography and like the latency isn't like high enough.
Yeah, no, thank you, that's cool. And I mean, that depth is part of why we're all here in Istanbul instead of at home.
Yeah.
The other thing, in your answer, you touched on, SOC 2 compliance, especially like with that, I mean, and stuff we're starting to hear a lot about like censorship in nodes and just, you know, compliance is now creeping into our beautiful like Garden of Eden that is Web3. And if anyone else is interested, there's a phenomenal paper outside of, I think it's the University of Athens, that looks at like malicious threat actors using Web3 as like a base for command and control servers and things like that. So I'm wondering from the compliance side, like you just said, hey, you're looking at, it's no longer agnostic. People say like, hey, I want SOC 2 data or SOC 2 providers, like with my IPFS to the side. I don't know, just do you have anything to talk to on that as any like nation states like we have now, what is it? Flashbots sensors and stuff, because, you know, based in the US and all that stuff.
I think this is actually like a really important discussion. This is like my personal answer, but also one of the two philosophical debates I had when I joined Protocol Labs.
Yeah.
I think it actually, there's two versions of the world. There's one where you don't censor anything and one where you censor everything, and both of those are horrible. Like, I think the thing that you don't want is to say like the worst things in the world are propagated. You also don't want to say like you are choosing what are the worst things in the world, because if someone else is choosing them, that could be quite bad. So I think like the only answer to that question is like, how do you allow individual autonomy at different levels? And like, if you are a storage provider, you are a business that operates inside of a country, like you will have to make whatever choices you have. But that's also part of an intentional decision then to separate like, one, like how do you reference content that does not require you to store things on that specific storage provider. Like you could also store things in a different country or not even on the network itself. You could just serve it yourself if you individually want to do that. Like, I think this is where kind of the beauty of the composability of the system comes in. like, I do think every individual like entity on the network should be able to make whatever choices make sense for them. And like, I wouldn't call it censorship to say like, if many people don't individually want to serve you, they shouldn't be required to. But then you always have the option to serve yourself or serve for yourself. And like, if you are offering your own content address data into the internet, like other people can discover it. And like, that's like, yeah, up to you and your prerogative.
Okay, so then I guess the censorship is left to the prerogative of data providers and everything that can be built upon IPFS and Filecoin.
Well, I mean, so like Filecoin itself, it's like every individual one of those providers. And remember, if we go there, Filecoin is answering this question of like what happens when you want to use a third party's like server. I think like it is always going to be at the prerogative of those people. But again, we're talking about like an open market. Like your routing path could also just push you through like other countries or places which are like more like friendly jurisdictions. It doesn't mean that like, oh, the only pathway has to be over with like one server in whatever location. So I think this is where you get the balance where it's like, yeah, everyone is making their own individual decision, but it also doesn't mean that you're locked into like what any individual has decided, which I guess is, at least to me, like balance. But yeah.
Thank you.
Yeah, so this is a more general question just about the Filecoin. So I've always been very passionate about Filecoin, and seeing your presentation, I think, just reinforces that. But like, thanks. So, but I think the one issue I face like trying to like better understand Filecoin is that like, for example, for Ethereum, how we learn Ethereum, we first like spend transactions, interact with smart contracts, run our own node, right? So figure it out. But that part is for Filecoin is quite difficult because like, right, for example, for our daily, average person's data usage, Filecoin, I don't think currently serves that. I interact with the Filecoins like at a sales team or whatever. They said my data demand is just too small. And also, I think our ordinary hardware is not able to actually do the data provider. So that actually hinders a deeper understanding of how things actually work. So do you have any comments on like if we want to understand it more deeply on a technical level, like how we go through learning Ethereum? Do you have any comments or suggestions on how to do that? Thanks.
Yeah, for sure. One thing I'll say is like Filecoin as an ecosystem is like almost like I won't say entirely orthogonal, but like it's a very different bet on like what are blockchains good for. And I think part of what made it possible to scale like the size that it has also applied taking a very specific pathway, which made it not so ideal for like the way that crypto normally sort of like builds up its sort of like following. For what it's worth, I do actually think the network is getting easier to use. So like there's a great app you can now download called Station, which is not storing your data, but it allows you to help participate in the network by like doing things like uptime checks. Eventually you'll be able to run other types of jobs on Station nodes. And like that's actually like the sort of thing where it's like getting a little bit more end user tangible. There's teams like Banyan who are also working on like different applications that work at different scales, teams like Web3 Storage, which work with the Saturn folks. So like there are more pathways for onboarding, but I do think like the UX is like a piece that has historically been really rough, but is like slowly getting shaved down in terms of like how it gets easier. In terms of learning more, I do think now that the FDM is there, there's more opportunities to build more like consumer-facing applications. Actually, I'll say like the things that I would put in the bucket of what makes building more consumer-facing applications easier. Once you have like small data onboarding / more small data use cases, things like Saturn can help with that, Web3 Storage can help with that, Banyan and Co can help with that. And then also when you have smart contracts, it gives like more places where people can like tactilely touch like the different parts of the Filecoin ecosystem. But I think as like more of these pieces get like built out into like things like Station even honestly, where it's like you won't get every compute load because it won't make sense to, but you might be the deploy target for something that can run on a laptop or something that can run in like less connected environments. So yeah, in terms of like the actual content, I would encourage you to go to filecointldr.io, where I write a lot of blogs, which has some of this stuff. But yeah.
To add to that, if you'd like to complain about anything that's hard to use, please come see me, and I will take those complaints and I will feed them back to the appropriate teams. Yes, thank you.
Okay, so thank you, Judy, for this.
Okay, everyone, please take a seat. So next is gonna start soon.
Cool. Hey everyone. Hey, I'm back. Victor, just a quick survey, because I just want to get a sense of my audience. It's a little bit of a different group than I'm used to speaking to. How many people in this audience have heard of IPFS?
Yeah.
Oh, good. All right. How many people in this audience have installed on a computer some form of IPFS software? Okay. How many people have heard of a content identifier? Okay, all right. I just want to get a sense of like what's our baseline, because it's not been originally given at an IPFS conference. My name is Hannah. I'm going to talk to you today about how we build IPFS systems that really work, that actually work. I've been working on IPFS, also Filecoin, for about 5 years. This talk is my attempt to share what I think I've learned along the way. Sometimes the lessons have been painful, and I'm trying to help you avoid some pain by sticking to best practices. Strap in, it's going to be an adventure. Also, just to let you, just a heads up, I do have a sort of irreverent, joke-heavy style of presenting, so just go with it. It's okay to laugh, or not laugh, because it's not funny. Cool. All right, part one, the dream. How do we get here? Why are we all stressed out? This doesn't have to apply to IPFS, but why are we all stressing ourselves out trying to make the whole internet work in a completely different way than it already does? In the case of IPFS, why are we trying to make it use content addressing? Or in the case of Web3 in general, why are we trying to do this completely new way of build a completely new stack for building applications on the internet? First of all, how did you all get here? I'm going to ask you. You can answer this in one of two ways, because again, it's a general audience. Why do you work on IPFS if you work on IPFS? Or why are you in Web3? Like, why are you not collecting a great salary, working for, some fan company? Raise your hand. Yes, in the back.
Cute PFP.
What?
The cute PFP.
A secure what?
No, the cute PFP.
Oh.
NFTs.
NFTs. Oh, yeah, for sure. We have better little images. They're right there. Yes.
Open networks.
Open networks, yeah. We believe in openness, believe in things that should operate together, not work in silos. I think I had one more over here. Yeah.
Yeah, I got a great salary in Web3.
You got a great salary to do something more interesting. That's actually a good reason. Well, let me tell you how I got here. I heard this is a research-heavy event, and I just want to give you some of my elite and awesome credentials that prepared me to attempt to completely rewrite core infrastructure in the internet. So first of all, I have in the past deployed a totally awesome inventory system to help the Gap send khakis around the world. Right? I've shipped a kick-ass loan qualification system for our friends on Wall Street at Moody's. Yeah, so definitely high-tech stuff. I killed it working on a website. Oh no, is this not coming up? Oh no. Hold on. It's even better when it works. I killed it working on a pretty awesome website for a bargain basement and Invisalign alternative, and I made the world a better place by working on an environmental social good investment platform for the young, liberal, and rich. And also I've worked on failed startups, like a lot of failed startups, so I just have some great experience. Okay, but somewhere along the line, in my case around 2017, I was inspired to do something different. Like, I imagine many of you have been inspired to do something different. Bizarrely, this inspiration is fairly well captured by a segment of Silicon Valley that I'd like to play for you. You can just roll. It's about 1:30. Okay, let's try this. Okay, hold on 1 second. I was told we have sound, but we maybe don't. We're gonna go back. Okay, hold on. Stop it. Yeah, we're gonna do this. We're gonna go back. All right, do we have sound here? Oh, no. I don't know how to do this on these touch things.
You probably know the lines. You can just I know the lines.
Is that high? You know what? I'm gonna try to do it all from memory, which I watched it a few times, so maybe I'm gonna, we'll give that a go. Let's see if this works. Okay. All right. Now I'm from Los Angeles, so this will be my attempt at acting. So basically, that character, Russ Hanneman, asks Richard, the other character, exercise. You have infinite money and infinite time and no constraints. What do you do? And Richard says, I want to build a new internet. And he's like, what? And then Richard says, well, listen, I got to thinking. I was looking at my telescope the other night, and Russ Hanneman derisively says, of course you have a telescope. And he says, we got to the moon using the computing power that fits now on a handheld calculator. And inside each of our pockets is a phone that has billions of times as much computing power as the computer that got us to the moon. And in fact, there's billions and billions of people with these phones in their pockets, basically doing nothing. So what if we took all of those phones and we used them to create a massive new network? And that network would use Richard's compression software to make everything super efficient, but it would have a totally new set of properties. It would be completely decentralized. It would be 100% private and uncensorable by any government or business, and information would truly be free. And essentially, that's the pitch. Russ Hanneman says, wow, I would fund that. Anyway, there you go. I tried to read. Yeah, Hannah Howard reading for the part of Richard. Anyway, also the whole clip, there's about 1:30 that goes into that I can play. You should definitely look the whole clip up on the internet because it's definitely not appropriate to play in a public setting. Because the jokes around it are pretty filthy, but they're hilarious. Yeah, okay, so a new internet, right? Something meaningful. Something that actually makes the world better, right? Not just saying it, but like for real. Something we want our names as people who are working on, as people who's taken up a career in this industry, to have our names attached to for a long time. So I want to talk about I gotta go there. Let's see if we can make all this work. Okay. All right. So I'm going to talk about my world for a bit. Over in the IPFS world, a lot of us set about writing a new internet, and we built IPFS. Came up with all this stuff. This is SIDs, content identifiers, libp2p, a whole peer-to-peer networking stack, IPLD, we heard about it before. It's an entire decentralized data format. UnixFS, a way to encode traditional files and folders into content addressing. CAR files, a standard for encoding verifiable data. BitSwap, a way to move all this stuff around. And IPNS, a way to deal with slightly more mutable data. And actually each one of these is its own giant specification. Like all those are new technologies that go into IPLD. And actually, that same is true for libp2p. There's like all those things. Even the concept of a content identifier is 4 different separate technologies. And if you're working in Go and actually trying to build something, there's a whole bunch of other concepts for like storing data on disk. And also, we built, to interface with HTTP, we built like 4 gateways for moving content address data out to Web 2. These are some services an IPFS node might provide. At one point, we even tried to write, before there was GoMod in the Golang ecosystem, we tried to write an entire Go package manager written in IPFS. So, yeah, super easy, barely an inconvenience. How many people, is there anyone in this room, raise your hand if you could define every single one of the things on this list for this group? Yes. Yeah, I've been working on it 5 years. I'm sure there's something in here I couldn't. Right? It's a lot of technologies. When I first started working on this, like I'm coming from as like a regular web app developer, and like the first thing I noticed, I'm like, there's nothing that is not built from scratch here. Right? There's like no in-use technologies. It's all new. It's all custom. Wow. and that was all both like totally intimidating and a bit intoxicating, right? Because you're like, oh my god, I'm doing real programming now. So yeah, I'm part of this story too because I've been working on it for a long time. This is like an abbreviated and semi-accurate list of things that I can say, yeah, I wrote that. So 5 years, that's pretty cool. And guess what? We built all of it, and it like works, which is to say, like, you know, kind of, you know, sort of, like, not, which is to say, not very much, but we're getting there. Anyway, so our protocols we're constantly involved in what we're doing, but we're still struggling, right? What are we trying to replace on the Web 2 side of things? These are the core protocols of the web. I think you can basically run a web server and a web browser with just these four. I don't know, maybe I'm missing one. If anybody else knows something I'm missing, feel free to correct me after the talk. So it seems simple, and obviously we have more names on our slide. So why haven't we won yet? So I would argue that we tried to build a new internet with protocols. In fact, the company that started everything in the world of IPFS is called Protocol Labs. But the internet is not protocols. The internet is infrastructure, like a lot of infrastructure. Okay, part 2, trains. So I'm going to do a brief digression, if you don't mind. A brief detour into another kind of infrastructure. I want to talk about building trains. This here is a public transit map for a major American city. Anyone want to guess which one?
LA.
Is it, what?
LA.
It's LA. Darn, oh man, I keep thinking I'm going to stump everyone. Because it's a very large network, and people think LA has no public trams. That's Los Angeles, that's where I'm from. LA actually has a large rail network, and we're building a lot more. Everyone thinks we love our cars, but we actually pay a full cent of sales tax to build new trains. The whole city voted for that. In fact, 2/3 of us had to vote for it because that was the rule. You needed a super majority to pass a new tax. So like, we don't have a problem funding transit. We want to fund transit. However, we are not actually using transit. Despite that, 73% of Angelenos still drive alone to work, and 6.8% I think now use transit. So that's a bummer. Why? Well, for starters, we already have this. We have roads, and we have a lot of them. And once you build something, it's quite hard to do something different. Our roads cost a lot of money to maintain. We pass the sales tax, but of that, about, I think, almost as much goes to maintaining and expanding the highways as it does to building new rail, just because they're so expensive. And also, LA is square mile-wise, like, quite a large city. And so the rail network looks really big, but it's not when you consider the number of square miles involved. Eventually, we might see buildings start to pop up right around the rails, but this network was built after the city was built. And so usually the hardest places to build rail are the places where the most infrastructure is already built up, where the most people are, because those people generally don't want their existence interrupted by giant trains construction for 200 years. So you realize the typical distance from and to a rail stop is on the order of miles. So what you're really looking at is everyone has a car. You can either drive 15 minutes, find a place to park the car, which may or may not work. You may or may not be able to find free parking. Take a train for 45 minutes and then catch another Uber for like 15 minutes. Or you can drive for 30 minutes or 45 in traffic, right? And for better or worse, LA is a car city. It's how we're built. And it's even kind of like part of our culture. Like we're famous for loving our cars. So we're trying to change, but it's really slow. And I think you can learn a couple lessons about infrastructure here, right? The first lesson is that infrastructure is harder to change than it is to build for the first time. The other thing you can learn is that infrastructure is not just what's built, it's what's built around it. So the fact that that most of our living is most of the places you want to go are not right next to a rail line is pretty important in how and why people don't use as much rail. And then lastly, that infrastructure is not just stuff you build, it's habits, it's culture, right? Okay, one more rail digression, and I promise we'll actually talk about web stuff. So this is China's high-speed rail network. By the way, if you ever just want to have a really interesting hour on the internet, do a deep dive on this if you're not from China. It's shocking. It's 40,000 kilometers of track, right? Larger than all the high-speed rail networks of the world combined. Transports about 2 billion passengers each year at speeds around 350 kilometers per hour. And it's been built in 2 decades. So, this is California's high-speed rail. We passed the proposition to build it in 2008, about almost 2 decades ago. It's not operational, probably won't be for real for at least a decade, probably more. When finished, it will maybe possibly move riders from LA to San Francisco at speeds of less than 200 miles per hour. So what happened? Why the discrepancy? Is this just further evidence that America is like a dying empire and its people have no shared purpose or some nebulous existential thing like that? Well, this is the U.S. interstate highway system, which is huge. It is actually more kilometers than the high-speed rail in China, and it was built in about the same amount of time, a couple of decades. So it's not like that, Americans can't build things anymore. It's just that there's some things going on here, right? Why? Here's 2 real reasons, I think. First of all, the rail network in China is driven by demand. China didn't have, before this rail network, China did not have infrastructure that scaled to its population, right? And this rail network is a pretty integral part of China's emergence as like a major world power. While the system itself is expensive to build and it actually operates at a loss, when you factor in the effect it's had on the Chinese economy, there's like one study that estimated it at about a 6% annual rate of return, which is pretty awesome. The city, what this rail network does is it does 2 things. One is it connects people who live in rural areas to urban areas, allowing them to join this sort of modernization effort. And it also helps turn like small cities that aren't the major economic centers into additional economic centers where there can be additional economic growth, right? And the net effect of this is that in the time it was built, I believe that economists now say that about half of China is in what's called the like middle income group. Sometimes in the US we call it the middle class. I'm not sure they're quite the same. But anyway, the middle income group is almost 1 billion people, right? In 2 decades, it was like 3% before. That's like amazing to lift 1 billion people essentially out of poverty. US, on the other hand, has a road system. It has an air travel system, right? If the California high-speed rail is not built, we'll still have a pretty darn large economy in California. So infrastructure gets built when there's a need. And we have something else in California. We have bureaucracy. We do a deep dive on California high-speed rail. You'll find that there's just like 3 local politicians and communities that somewhat annihilated the potential for the entire project. It was either by refusing to let the rail go through somewhere that it really needed to go through in order to be successful, or it was by diverting the rail to a city that really didn't need it, because that local politician could say to their constituents, look, I got the rail, but then that made the whole system like way harder to build. China, over the last 2 decades, has not always had this. The government has been able to sort of just mandate the building of these rails, right? And so you get very different results. This isn't always a good thing, both in the case of the US interstate highway system and the Chinese rail system, this ability to just mandate quick building had some negative effects, at least in the US. It destroyed a number of communities as they just built highways through different areas and lives in the process. But you can just see that there's a difference here, right? And it's about the fact that infrastructure is not just building, it's not just building objects, it's about building consensus among people. Make sense? Yeah. All right, cool. Back to the web. Yay, thank you for going on that adventure with me. Part 3, building blocks. So what are the building blocks of what's the structure of the internet? What is the actual infrastructure? Well, for one, there's a lot of computers, big servers. There's also a lot of switches and routers. That is a picture of a Verizon switch center. It's also a whole bunch of high bandwidth data trunks that move data around very fast. Literally, these data trunks are often a series of tubes. For those of you guys who are in the US and know that that was derided, is not what the internet is, but that's what it is. Those are the underwater cables that connect across the continent through the Atlantic Ocean. So yeah, those are all the physical infrastructures. And if we take what we've learned from trades, it's not just what we built, it's what we built around it, right? It's browsers. Browsers are like huge, highly complex, and highly optimized software for reading the internet as a client. It's also web software like Apache and Nginx, which are highly optimized software to serve data on the internet. It's standards bodies like the W3C, standards bodies which now have a number of members who have vested interests, and sometimes you do see bureaucracy there. And it's a set of ideas and design philosophies. Mostly this guy's ideas. This is Roy Fielding, the creator of REST. For them, if you've ever heard of a REST API, that's what that term is originated in, but it's actually a philosophy of building a massive network. And for years, I derided that word as like that's what the purists are into. But like when you get into trying to rebuild the internet, you realize this is the caching strategy of the internet. This is what enables data to be moved around a massive network of billions of nodes, right? That's why it works at massive scale. So what do we have? This is going to be very IPFS specific. What actual infrastructure do we have in the world of IPFS? And you can probably generalize some of it to Web3. Well, we have, for starters, 250,000 nodes that are running IPFS and the IPFS network. That's not nothing. That's a pretty good start. Probably more impressively, we have, as Jonathan mentioned, exabytes of hard drive space waiting to be filled up and used to store content address data. That's pretty wild. We have a bunch of investment. Billions of dollars have been put into building a new internet. That's important, and there's still a lot of that to work on to try to build more things. We've got, you know what, I just skipped over one. I'm so sorry. You're probably noticing the bullets are off. We have hundreds of software developers working on this. Like people who've been working together for a while, starting to build really good relationships, starting to think through problems together across several companies in a somewhat decentralized way. And in IPFS land, we have 10 implementations of IPFS. We have an IPFS that goes to space. Seems like we've got a lot of software built. We're sort of interplanetary, right? This is sort of the core part of the talk. What I don't think we have, that the web has, is a set of technologies in the world of IPFS that go together so well that people start to build killer apps on top of it. So that billions of regular people start to use IPFS without, oftentimes in like a ideal world where our content addressing or our Web3 primitives are truly successful and adopted. Most people don't know that anything has changed. Most people don't know until maybe ideally some government tries to censor their stuff and it doesn't get censored, So that's where we want to get to. But to get there, we need people to be able to build like web scale applications on top of our platforms. And we're not there yet. I would argue that our problem is not that we don't have enough technology. We have a lot of technologies. in content addressing, in IPFS, Filecoin, Web3. This world is full of new technologies. You can spend like a week learning new jargon. In fact, what I think is fewer technology. What we need is fewer technologies, but they should be the key fewer technologies that go great together to enable things you couldn't do before. So, part 4, systems. Recently, I saw this. I can't remember this slide. Oh no. Oh, this slide has no content. It's just me speaking. So, what's a system? Recently, I had a debate. There's a gentleman named Brendan who works on the Rust implementation of IPFS. And he stopped talking about IRO, the name of this product, as an IPFS implementation. He started saying it's an IPFS system. And we ended up having a debate about whether IRO was an IPFS system or an IPFS implementation. And he argued that IRO is not an implementation because it does not interoperate with Kubo, which is sort of the original implementation of IPFS. And I argued that's not what the specs say, and we've gone through a whole process where we tried to make it a lot more loose so that everyone could say they were an implementation. We went back and forth. And later, I wondered about systems. What IRO actually is, which again, it's an IPFS, the Rust IPFS does not interoperate with all the other IPFSs, but what it is it's a cherry-picked set of IPFS technologies. Some of them are old, many of them are very new. And they go together to form a product that is really quite a great platform to build applications on. I'll talk about that in a second. So what we might need is not IPFS implementations, but systems. Ways of putting the pieces together that enable highly scalable applications to get built. And this is the core point of the talk. What IPFS systems have been built that you can build really amazing applications on top of. So let's look at some, these are just like a cherry-picked set of things in the IPFS ecosystem that I think are really cool. The promote other people's stuff section of this presentation. So first I actually want to talk about this thing, IRO. This is this Rust IPFS. IRO is very optimized software, right? IRO is written in Rust. It's designed to run IPFS on any device. One of the chief complaints that people make if they run Kubo, the original implementation of IPFS, they say my computer stopped running because you consumed all of the memory and the CPU. Obviously not a win. IRO is written to run anywhere, including specifically, it's one of its primary targets is mobile phones. It has very limited ways of transferring data around and hashing. These are like big choices to make when you're inside of building an IPFS application. There's only one way to move data around, and there's only one kind of hashing. It's all essentially built on a type of hashing algorithm called Blake 3. I'm not going to go too deep on it, but that's sort of unusual because they're just saying there's only one way to move data and only one way to hash because we think this is the optimized way. They have a custom and fixed network stack. They do not actually use libp2p. They essentially just build on quick. The focus for IRO has only one focus, which is to move and sync bytes, essentially to distribute files and then synchronize collections of files. That's it, right? And what they've managed to do, what these guys put together, is they built this platform that is a really awesome way to synchronize files across devices or even to synchronize collections of data. They have essentially built an IPFS Firebase. And it's pretty cool and highly performant. So that's kind of awesome, right? Let me talk about another technology that is in the IPFS world that I think is really interesting. That's this technology called UCAN. It was originally developed at Fission. The next speaker is going to be from Fission, and it was built out a lot by a group called Web3 Storage, which is essentially UCAN is a system for tracking the chain of authority across an IPFS network. What that means in simple terms is UCAN's like a JWT extension, right? Raise your hand if you know what JWT is. Oh, okay, all right. JWT is a very simple way of passing around authorization on the internet. Raise your hand if you've heard of OAuth 2. All right, yeah, okay. OAuth 2 is delegated authorization, right? It's essentially, and UCAN is a much simpler form of OAuth 2. It's a way of verifiably saying, giving someone a token that says, the person doing this operation is authorized to do it. But the delegated part means they're authorized to do it by someone else. And they're only allowed to do certain operations as authorized by someone else. You get this chain of authority. And UCAN is not just authorizing access to data or operations on data. It is actually authorizing, oh no, I did delegated. It's authorizing the ability to perform computation, right? It has this concept of delegated invocation, authorized invocation. Moreover, it can actually get receipts that an authorized invocation has been run and results from that computation. So what you end up with, and I realize this is a little bit theoretical if you haven't really touched a lot of this stuff. You add one more technology, which is called a decentralized identifier, or DID. This is something that allows you to make your login just something like rather than an application having a list of users. It's simply your decentralized identifier is simply your email with someone attesting that you actually own that email, right? It could also be your crypto wallet with a proof that you can sign a message on that chain. And when you add DIDs and UCANs, what you end up with is this system for essentially hiring arbitrary services in the decentralized web to work for you. So you look at Web3 storage, which has implemented all of this. They give you a command line tool that allows you to take your data and upload it into potentially any storage provider. Right now, they're the only implementer, but it's a totally open spec. And Web3 storage does not have a list of users. You are the user, you control your decentralized identifier, and you can associate potentially a credit card with that identifier so that they can charge you if you want to store a lot of data, but you pack your data, you verify that it was content address, you can even use it for a whole platform where, like, what's it called, OpenSea needs to let their users upload data without actually giving all of their users, their private key, right? So they use this delegated authorization to allow users to upload data on their platform, right? And then move it to Web3 storage with their users not actually having Web3 storage accounts and without Web3 storage having an actual account for OpenSea. It's pretty wild, and then that can keep going. You can go all the way on to Filecoin, and probably in the future we'll link it up and it can be used to authorize retrieval from Saturn, which I'm going to talk about in just a second. I think Jonathan mentioned it briefly. It's this lovely company that I want to mention. What they're trying to do is provide an enterprise-grade storage product, something that companies can hire to store terabytes of data. And what they do is they use another technology in this world called WinFS, which I think there's a talk on coming up. Yes? Oh, you're gonna know what this is in 2 seconds. It's a way to take all of your data and make it content address and also encrypt it in private, right? So no one can read this. So they use this software to take data and make use WinFS to encrypt it and make it content address and pack it into car files. And then their actual storage network is Filecoin. They don't actually have any of their own storage. They use Filecoin. They contract with specific storage providers who are willing to run custom software and sign contracts to perform really well. And what this does is it enables a working, private, enterprise-grade storage system that's completely decentralized. It's pretty cool, right? Finally, I want to show one shameless plug. This is the only part of the talk where I'll talk about the thing that I work on. So I work on this thing called Saturn, which is trying to we're putting components together to unlock a CDN that you just can't build on a centralized network, right? So we use, again, content addressing. All of the data we work with has to be content addressed, right? And we have a network of nodes. And these are people that have signed up to join Saturn. They have computers either in data centers or other places with high bandwidth connections. But we don't like contract with them at all. They are members of our network. We do not rent space in a data center. And they run an optimized IPFS fetching software called Lassie to get content address data from the networks, from IPFS and Filecoin. They pull stuff in and then they cache it, right? We have a simple piece of JavaScript to run in browsers in order to make requests to our network and get this content address data back and then verify it right in the browser. This could also happen in a native application. It's actually kind of easier if it does. But what this means is that you request content from the Saturn network, and untrusted nodes send you back data. But they can be untrusted because you immediately know if they tampered with the data, right? Moreover, we have like a crypto-economic model in which essentially it's based on metrics, reconciliation, and fraud detection for now, similar to the way like ad networks work. But essentially our clients and our nodes report back data on what they're serving, and we run a bunch of reconciliation on that to find out who's serving content and how well they're serving it, and we reward people based on how well they serve content. And that lives in a bit of orchestration software, which for now is centralized, but maybe not in the future. This is what it enables. We launched 1 year ago. We currently have 25 terabits per second of data bandwidth. We serve about 1 billion requests a week. If you want a comparison, Cloudflare, fairly well-known CDN, probably one of the largest, launched and reached 25 terabits per second of data bandwidth in 10 years. We got there in 1. So, yeah. Yeah. It's exciting, right? Because and the reason is because anyone can just join it and, come online, right? And one of our particularly enthusiastic team members says that when we go to sleep, the network increases in size. And sometimes it does. Cool. So yeah. Now, I don't know how many people in here are true decentralization purists in the audience. There might be some doubts that are creeping in, right? You might be like, oh, I heard a centralized component in there. Oh, about that. Oh, wait a second. I heard one of your implementations isn't interoperating. I don't know about that. Well, yes, there are trade-offs. Yeah, there's not much we can do. There are trade-offs, and some of those trade-offs are often painful in order to get towards the vision that we're building towards. Even though large portions of these systems are completely decentralized. So the last thing I want to talk about is people, because we're all trying to build these new systems. If you're in Web3, whether or not you're in the IPFS Filecoin ecosystem, or if you're in Web3, we're trying to build new things. It's a much harder form of software development than if you are someone like me who spent most of their time building web apps before this. And so I basically have 3 last qualities that I want to say, what do we need to get there, right? Because we have trade-offs and they're painful. And we need to treat each other well as a community going forward so that we can get to where we want to go. So I have 3 qualities that I would love to see more of in Web3. The first is humility. This is a hard lesson that I've learned. I don't know what I'm doing. Does anyone here, some people, there's probably 1 or 2 people who just sort of see the future and move forward towards it. I'm not one of those people. Trying to build the right thing, it takes a lot of trial and error. And so I encourage everyone, if you're in this world, learn some humility, because you're going to find out you're wrong a lot. The other thing that I've noticed, I can't speak for other ecosystems, in IPFS, one thing I wish we did a little more of is listening to each other. There's sort of like, there's a healthy competition among a lot of our teams, and that's great. But sometimes there's like, we're so sure that we're doing it the right way that we don't hear the other teams and how they're working and how that makes, what we could learn from them. And I think we could move a lot faster if we did that. And the last thing I think we need is patience. This is going to take some time, and we need to trust each other, especially as we are all, building new products and building things that enable the next version of the internet. So, yeah, that's me. That's my contact info. That's the Saturn team. You can, if you want to know more, since I know that wasn't the focus of the talk, feel free to talk to me after the talk. I just put this slide on here because these are some humans in my life. There are humans and animal. That's my partner Ileana and my dog Sadie. So they get a special feature because they make my life worth living. Okay, that's it. Cool.
Does anyone have any questions?
Yeah, so when you say there are 10 plus implementations of IPFS, can you define what implementations are?
Yeah, hence the debate that I had with my. So technically, the IPFS spec says that sort of like very limited scope nowadays to be defined in order to be defined as an implementation, and that is that you need to work with you need to support content address data. That needs to be your primary primitive, and you need to transport data in ways that are independent of the underlying protocol. I'm not crazy about that one. So it's super abstract these days. It used to be that IPFS, define an IPFS implementation was like, you have libp2p, you have bitswap, you have like as your way to move data, you have, you have an HTTP gateway, you have like a bunch of stuff, and they cut it down significantly to allow for experimentation, but yeah, it's very poorly defined. I'm sorry that I don't have a better answer for you, and I'm like someone who's been working on this for a while. I didn't actually write the super minimal version of an IPFS spec, but for me, anyway, it's like if you work with content address data, then you're IPFS, for me. Like that's what I'm working on, so that's what drives me, yeah. Cool. Other questions? Yeah.
I think you kind of raised a lot of important and interesting business questions at the first half of your talk. So, and I'm just curious about how does the Protocol Labs, how does the evolution of the business start? Like, there's a lot of coordination problem. You need to build A before you can build B. There's chicken net problem. How do you actually solve these problems?
So, yeah, I mean, and I think, I have to be careful here because what is Protocol Labs doing should be an authoritative answer from Juan Benet, who's like the boss man. But for me, I think we traditionally in Protocol Labs for many years, we would build for a while until we encountered a problem, right? And then we'd be like, oh, we need, to your point, this needs to exist before this needs to exist. So then we'd spin off a little team that was working on that, on the thing that needed to exist, and the other team would sort of try to coordinate with them, as all within a giant company roadmap. And that has been really annoying, and especially for everyone in the ecosystem, because to have the context, you need to be in the company. And we're not really doing that anymore, because I don't know if you've followed, but Protocol Labs is spinning off a lot of its own teams in their own little companies. I would argue that we actually, in many cases, not all cases, we are and this is again what I'm talking about. We're not in the moment where we need to build this thing for that thing to exist. We've got enough things, and to build some cool systems out of them that then allow people to build applications, right? So all the things I talked about are not they are not products that are applications. They are platforms from which you could build applications, even though they're cherry-picked technologies. Sorry, I realize this is kind of a lot of layers. And to me, that's what we need, is people looking at the whole thing and saying, these 5 things would go together really well to enable this type of application to be built. And I think that's what we could do. There's a lot of centralization points that we still end up on because a thing doesn't exist. Like the Saturn orchestrator that coordinates the whole network. Sorry, I'm just a little bit freewheeling this. That is centralized because we don't have a super scalable compute, decentralized compute layer within the network at the moment that is verifiable, which is what we would need in the case of Saturn because it's dealing with money. So probably we are going to wait for IPC, and now IPC is going to be a different company from Protocol Labs. And Saturn's going to be a different company. So that'll be interesting to see how that plays out. So, yeah.
Maybe they give a different version of that answer, because like, I think Banyan is a good example of this, where it's like, Banyan is working on top of a number of different teams with a number of different technologies. And so I do think you see, like, the thing I actually think is maybe the positive for anything like that is it forces more of this coordination to happen external to PL as like a group in like the ecosystem, and like everyone kind of knows each other. I mean, not everyone knows each other, but like most people know each other. And like I think the more people coordinate on these problems in public spaces, it also means that there's like a broader set of input on like what are the actual problems that need to be solved, not like in one specific version of solving the problem what that means. So yeah, I mean Banyan is a good example though, I think, of like taking from like the IRO team, from you guys, from the OneFS side, and UCANs, and like even the Filecoin side, like trying to piece all these things together.
Yeah, and like I'm not kidding you haven't followed like major portions of the current Protocol Labs company are going to be becoming independent teams and independent startups. So we're going to be moving to an ecosystem model, a true ecosystem model, whether we like it or not. And I think teams like, Fission and Banyan are like, oh, welcome to the party, finally. Yeah. Yes.
Hannah, as a former application developer, somebody who's building apps for end users, and thinking about what you're talking about infrastructure and the need, it's built with a need in mind. What have you imagined what types of bits of like IPFS, Filecoin, et cetera, that would be leveraged to be able to build apps that fill a need that cannot be filled by current like Web 2 style things? So what, just thought I'd throw that out there.
There's God, wish Mosh Michelle was here because she's got like a list of like these are 4 categories of you put these somebody needs to put some components together to enable this kind of application. But okay, here would be my quick take. Like very large asset distribution is one that's in my head a lot, particularly for Saturn, because content addressing. If you think of like we haven't really gone too deep on what exactly it is, but you can vaguely think of, having content addressing being like you have your data, and then you essentially have a Merkle proof on top of it, similar to BitTorrent, right? And what we know is that BitTorrent is actually pretty good at moving things around very fast for large amounts of data. And I think that through IPFS and maybe some infrastructure like Saturn, you could do massive asset distribution, which is increasingly quite important in the world of gaming, because now they're like, hey, I don't know if you all follow that, but like Unreal is like, you know what, you can have no polygon limit if you want. You can just build assets that are like your production assets for a movie. Sorry, I'm going a little bit. And my first thought when I heard that was like, well, yeah, but how are you going to pack that into like 70 gigs of data that you can download, right? So you're gonna probably see a lot of asset distribution stuff. I don't metaverse there. But there's a whole other class of things, I think, in like censorship resistant applications. I don't know myself. I'm not sure I can tell you what the exact set of technologies you want to put together to do that. But somebody should pick that up. If you want to start a startup to do that, there's a market there. There's other ones. Again, Jonathan, do you have anything?
I was just going to say, actually, I don't think the right framing is like, what are the things that are only uniquely possible? Because I do think one of the biggest uniquely possible things is like, can you get the cost lower? Like, there's a lot of teams, like, I was chatting with the HighMapper team as an example. Like, their biggest, like, they do generate, like, quite a lot of data, but their biggest cost is actually, like, what? Because they're serving a lot of data as well. And so, like, all of the content addressing stuff is really just unlocking the thing that Hannah said, which is, like, how do I have magically more servers that can stand up overnight that can potentially serve this at a cheaper cost? And I think, like, over the long term, at least my personal bet is, like, the big killer feature is, like, can you just be cheaper and still serve these things?
There's for sure money.
To your point, I was just like somebody had sent just passed me this article from The Verge today, which says Baldur's Gate 3 Deluxe Edition on Xbox and PS5 is coming on a fuck ton of discs.
Yeah, it's not a CD-ROM anymore, you know, like, no, yeah, magnetic tapes, underused. Yes, sorry, we have a question back here.
I have a very interesting idea to share. It's actually last week, the Cloudflare got temporarily banned in China, causing like Taobao, like Alibaba, like Amazon, like bunch of websites basically down. The reason behind it is the CDN of Cloudflare, the root address is 1.1.1.1, right? Like they got banned because bunch of people are using it to bypass, using protocol like B2Re or Reality to bypass the Great Firewall of China. So the interesting thing is, if the Satchel can like have a decentralized CDN and building some protocols to like to allowing people to bypass like the Great Firewall of China, then you can basically get millions of users directly. That is internet freedom is the thing, right? Like.
Yeah, we've been having some conversations. I mean, again, this is like, and also like IPFS and Filecoin have like tremendous interest in, I mean, particularly Filecoin, but like, yeah, I mean, I'm sorry, I'm chuckling at the idea that they're like any cats they came to fit them in the butt. Because literally every Cloudflare center has the same IP address because it's just like hack to make your content go fast. Yeah, I mean, I think there's a huge opportunity there. The interesting question is, will you be able to decentralize it enough that people can't find ways to shut it down? So, like, for example, we have this orchestrator. I'm just thinking through this. And we have an orchestrator that collects all the metrics and then bans nodes who perform badly. Well, the problem with that is that means that if we were to run it in China, like the same, you know, the Chinese government could come and say to us, hey, your orchestrator needs to ban these nodes, right? You know, so like that's it. You know, there's a number of ways we could work around this, but like, yeah, I think there is a possibility there, but it's definitely, the proof would be in the pudding to see if we could do it. You know, but I think there's I mean, like, we've been talking to folks about running, like, you know, starting to grow the Saturn presence in China, because I think a lot of our stuff is still, actually we do have some presence, but it's not, like, compared to Filecoin, which has like, the biggest Filecoin providers are all in China, like that we're not quite as far along there.
So related to the censorship, like was that event like in Turkey, like some censorship and then IPFS put the Wikipedia on?
Yeah.
Are they any follow-up? What happens afterwards?
I mean, so that's an interesting thing is like, that was, yeah. Basically what happened here is that, I believe Turkey's government made some edits to Wikipedia. No disrespect, Mr. Aragon. And I believe at the time, Protocol Labs had copied and hashed a previous version of Wikipedia without those edits. And it was essentially published on IPFS. And once it's published, technically anyone can host it, and it may be harder to take down. The harder thing about taking it down on IPFS is, again, because it's content address, if you know that hash, and then somebody hosts it, and then Turkey says, hosting provider, take it down, and then somebody else hosts it, nothing changes, right? Because it can move around without anybody shutting it down. And that was how, I think, another example, they basically held like referendum on independence for Catalonia in Spain on IPFS. Protocol Labs, the company, no longer gets real deep into some of those political things because, you know, there's a lot of liability now that they're a little larger. But yeah, no, it's still, things are possible. It's not a catch-all though, just to be clear, like, you know, doesn't matter. One of the biggest conceptions about IPFS, misconceptions, is that when you put something on IPFS, it will just last forever. You know, that's not true unless, because if only one person has the content and they go down, now it's gone. But if someone else has it, they can put it back on. Yeah. Cool. Okay. Sorry. Thanks for taking.
I'm going to speak speed run my presentation a little bit because I know that I'm sitting between you and dinner, and you really want to hear about Philipp's crypt tree. So my name is Boris Mann, and I'm the founder and CEO of Fission, and I'm going to talk to you about life at the edge. So Fission is a company that specializes in protocol-first applied research and software engineering. Basically, there's deep tech and other things and software often is seen as something that's easy, but we took an incredibly hard route, although it's been a lot of fun along the way. I wanted to kind of throw this up. This is something that I say a fair bit, and sometimes I say it even more, and I say like IPFS has won, but we're actually changing what that means as well. And what does winning look like? So from a Web3 perspective, ultimately at the end of the day, there's like shared components really low down, lots of things. We use libp2p that Protocol Labs helped do with the Ethereum Foundation, and all these other pieces like cryptography libraries and other stuff like that. And when we pop up again, there's lots of competition. And content addressing kind of sits in the middle. It's not tied to any one chain. You can produce it locally, it's locally verifiable, and we can read and write into this global namespace. That's freaking amazing. It's actually a really great low-level thing. And one of the things that Hannah said, she's like, yeah, but if it goes offline and it's gone forever. But it isn't, because if anyone anywhere has a piece of content on a USB stick, on a CD-ROM, or anything else like that, if you plug it back in again, that content address is still the same. And that is super, super cool. And if you're really deep into the IPFS ecosystem, then you know that Drake is mad at old CID version 0 QM hashes, and that BAFI addresses are super cool. And because there's only laughter from like the IPFS crew, we know that you haven't been totally IPFS pilled, so we will work on that. So Fission has been going for 4 years. Because we in fact have had to build a lot of things. You might know some of our protocols and our cute mascots. UCAN for decentralized auth, WinFS for encrypted file systems, and IPVM, the interplanetary virtual machine. And we'll talk a little bit more about that. We've done a few other things, securely linking devices so that you can pass keys around using something called Awake. We're going to switch to the IETF MLS at some point. Carmir, which is an alternative to BitSwap to make things go fast and do partial syncing over Carmir. Philipp, I think you're going to cover some skip ratchet stuff. Sure. Great. Yeah, a pile of tech. So what's been great in working inside an ecosystem, and literally everything that I have on here has been mentioned before, which is super awesome. UCAN and WinFS came first. And so they've had the longest time to have adoption and diffusion throughout the PL network and beyond. So some of the teams that have implemented or integrated the protocols include IRO, Subconscious, Banyan, Web3 Storage. Our friends at Saturn, I think, are going to end up at UCAN at some point as part of the things. And I think Fileverse is in the room here today as well, who's doing some interesting stuff. Plus collaborators and standards groups. So this is not us doing it all by ourselves. All of this stuff has been done in open working groups, both informally from bottom-up community protocols, and then standards groups like the Chain Agnostic Standards Alliance, and soon some new work in the W3C. So some of those things are structures that Hannah mentioned as well. So now I'm going to tell you a little bit about Fission Original Mission Edition. So Brooklyn Zelenka, my CTO and co-founder and good friend, started Fission after spending time in core Ethereum space. So Brooklyn was a core EVM developer, and I helped run and start the early Ethereum magicians and the early unconferences and organize core dev events. What we found that a lot of people had challenges with were like, okay, there's this new tech, there's Solidity and smart contracts and security, and that's all brand new, and we have to figure that out. And then Web3 devs would like go to build a web app, and we'd be like, Brooklyn and I have been building these things for decades, and we're like, it's the same problem. Everyone's running straight into having to become a full stack developer and do identity, data, and compute, and DevOps. And put all that together. And we said, what if we just took a lot of these advances of Web3, of distributed systems, of cryptography, with content addressing as a base, and we put the entire front end, that entire stack, directly into the front end. We do that in the browser. And it just makes no sense to have this completely decentralized back end and then run a Node.js app on top of it. Single point of failure. What are we even doing? Plus, it's just hard and expensive. All of the scaling is on one team. So, life at the edge. A lot of the stuff we've talked about is with blockchains is spending a lot of time working on logically centralized systems and global state. And you know who's at the edge? People. That's where all the stuff is. And in fact, this goes back to the Silicon Valley sort of thing. And we really think that there's an opportunity there. First of all, we have to always be thinking about that. People want their stuff with them all the time. One of the things that I really hate about IPFS is this thing called pinning. It's filled with lies. It doesn't make any sense. And most operators who run IPFS nodes at scale turn off completely the garbage collection that was its original purpose at the end of the day. Ultimately, people want to have their stuff, and they want to have it available, and they want parcel sync to get to it. And the promise of the cloud within Web 2 version is mostly siloed. So Web 2 platforms where if the app developer goes away, and maybe they go away because it's really expensive to operate, so does all of the user's data. And you have no idea if they're peaking, right? Like, yeah, it's in a database, and really you have no idea if the developer's looking at it or not. So April 2019, paper and a bunch of research by a research team called Ink and Switch about local first software. This has been done before, it's been written about before, but this really reinvigorated the space again and had these 7 ideals for local first software. Again, not something we talk a lot about in blockchain space because there's this vast global infrastructure that's logically centralized. Plus we're trying to fix some RPC stuff. And then, but the data at the edge is actually the important part. So these are really, I think these are really good principles for to think about at the edge. And what I started thinking about is okay, let's protect all this data, let's encrypt it end to end. Really, in many ways, what Fission has been trying to do is say, that really luscious end-to-end Apple stack, we have to rebuild it. Because it's completely proprietary, it's tied to their hardware, and we can't reuse it. So I'm actually this whole company is actually just me being mad at Apple because they have really good UX and good patterns. But so we have no choice but to turn these into components that we can reuse. What I'm now worried about, as we're actually getting pretty good at end-to-end encryption in many situations, is silos. So if we don't work on interop, then end-to-end encryption of data means you've got system A that has a particular system for doing end-to-end encryption, and system B doing end-to-end encryption, and system C that does the same thing. And what does the user have to do? Decrypt it and move it between systems. Unacceptable. The way this should work is we should have an open source iCloud, Dropbox as a protocol. And by the way, we should also be thinking mobile first. So many people in Web3, so many blockchain developers sit there with giant monitors and professional desktop operating systems, which are dying, and design things. That's the other rant that I've had for many, many years. If we can't carry these things around in person in our phones, we're not serious about building a new internet. The new internet needs to be mobile. So, and that pattern actually already exists in native mobile. When you pull up an app, it says, hey, can I access your stuff? And we give a capability for that app to do that. And that's where I'd like to get to with encryption. If you're working on anything related to encryption and personal data, we need to figure out how to interoperate. So I'd love to talk more about that. UCAN for capabilities, WinFS for interoperable encryption. if you're not following some of these standards, these are some things that are coming along that are really, really great. How many people in the room have heard of the chain agnostic standards lens? Okay, fantastic. I'm introducing it to you. Search for chain agnostic. Basically, a bunch of people started with Ethereum core group, really as it became clear that we're going to be many EVM flavored chains and many Cosmos chains and many other chains. And then, in fact, what we should do, instead of continuing to solve these problems independently, a lot of this came out of wallet developers. I was at the running the wallet unconference today, because it sits between app developers and users and the kind of the rest of consensus core for things. One of the things we figured out is blockchain, largest deployed system where people already have public-private keys. That's amazing, right? 50 million accounts, whatever we're looking like there, pretty good. And what we need, however, is we need a wallet standard, including for my friends at MetaMask, that lets us use encryption keys separate from signing keys. So end user encryption, decryption, turnkey with all of the wallets that are already deployed. And we can get there. We're actually getting quite close to that. So working on that with Brave, MetaMask, and other wallet devs. So that's something that's in action. How many people have heard of passkeys? Handful. Passkeys is big tech, WebAuthn, but also standards. That also is another mechanism where direct mass market end user managed access to public-private keys. There's a few little standards. It works in browsers, including on mobile, but that's coming along, and a lot of people are working on it in different ways, and I'm super excited by that. Something that Protocol Labs helped make happen by going back in time 4 years ago and spending time and advocacy and money and examples is ED25519 curves in all browsers, including Safari. Can I get a whoop whoop for new curves? Right? And that's what it means when we work together. A lot of that was talking to people and saying, what do you need it for? And working with the W3C to say, oh yeah, this is important. So we wanted to build this stack for front-end devs to build apps that compose really nicely. But we actually find ourselves in the protocol mines because we're like, oh, there's a few pieces that need a little tweaking with IPFS. And we need a decentralized auth standard, just like OAuth and Twitter kicked things off for APIs, REST APIs, back in the mid-2000s. We need identity because we want to do encryption, and you can't do encryption without identity. So then the new thing that we've gotten to now is IPVM. The whole thing of identity, data, and compute, we're building those pieces to get to the interplanetary virtual machine. So this is an example. Again, we're working with the wider PL and IPFS and Filecoin ecosystem. A specification for bringing content address execution to content address data on IPFS. So skipping a few bits in the middle, why not build a competitor to AWS Lambda? That's the open IPVM working group. You'll see a lot of the things that Fission works on are not under a Fission namespace. They're not ours. It's work that we do and working with other people. The original spec was co-written with Bacchiao, UCAN Invocation, which is, Hannah mentioned, a ton of work with Heracli from Web3 Storage, and that pattern continues in everything that we do. Banyan decided that they wanted to work on enterprise sale encrypted data and added those capabilities to NFS. Well, we were focused more on personal scale. Amazing. Let's share engineering resources and make sure that it works well together. There's a ton of video deep dives that you can go to at that address. This week, the Fission team worked together to take all of these things, take these protocols and pieces of implementations we put together and build a platform. So this week has been the launch of the Everywhere Computer. And this is kind of like the Red Hat of computational networks. Fission's going to run it. We're going to brand it. We're going to have a distribution or system. I think some of those two words have some things in common. Bundles Homestar, our Rust implementation that focuses on WebAssembly, a control panel, a function and workflow marketplace. So think like NPM, but like filled with WebAssembly functions. It's almost like edge smart contracts, and manage compute resources. So as a developer, write functions and integrate custom services. As a user, bring your own compute or rent ours. As a computation provider, bring custom resources and register them with the network. So John talked about data gravity. If you have a few little bytes, or maybe it's really big and it's megabytes of functions, why not send those over the network to run computation next to where the data is? So some of this capability actually starts breaking down some of those large clusters, and then you can move them on around as well. So as an ecosystem, I also see basically whether it's app chains or IPC or other specific applications deciding that they want to federate their own network of functions, services, and resources that matter to their. And I think that's the thing. We're turning a lot of things into markets in a good way. A little bit of a taste into future work and research. Videos, oh yeah, I'm not going to play the video, but this is about a 10-15-minute video where Brooklyn Zelenka essentially speed runs what we've been working on, where the future is happening. Highly recommended. That was at EthCC last year at Blue Yard side event. And really talking about what goes on-chain, what goes off-chain. And I think with IPC and FVM and content address data and the stuff that Fission are working on, that's really fuzzy, and that's what content addressing gives us. When the content can't lie, it means you can move it around and do proofs around it really easily. IPFS payment channels and a web services-focused decentralized billing system. We're going to run an open web Amazon, then we actually need a billing system that works within a decentralized context. We designed the IPVM alongside of the FVM team. Our stuff is also written in WASM and Rust, so again, that on and off chain means we can collab really well. We're going to be working on integration into ecosystems, app chains, L2s, mainnets. A number of people from launching this week are super interested, and I'm excited to see where that goes. Finally, WASM from browsers to servers. So we are going to be launching a W3C community group, and we've got teams from within Intel and Google interested in participating and going through the standards-based process. So I think there's this other continuum of on and off chain that is Web 2 to Web 3, where everything slowly comes together as part of Web 3. That's the end of my talk. Speed run.
So thank you, Boris. So a question? So maybe...
Perfect, speed run. On to you, Philip. Or do you want to ask me a question before I run away?
Yeah.
Okay.
So how about the downtime for the Homestar?
Downtime for Homestar. How many nines are we going to get? Really interesting. I was talking to the DRAN team. They have 100% uptime for 4 years.
Okay.
I don't think we're quite ready for that yet. We're just launching the first version of this. What we really see is, again, a larger network of nodes available, all with the basic capabilities. So what we've decided is all Homestar nodes will be able to run WASM functions. Some nodes may have extra capabilities. So like John mentioned, some nodes may have lots of GPU. And if there aren't that many of them, your job may not be able to execute. But from a WASM perspective, even your browser can execute that WASM. So we should be able to route to someone, including just someone nearby in like a cafe or something, that can execute for you. TBD as we launch it.
Yeah, and there's no like incentivization layer.
All of these are layered systems at the end of it. So we think that an IPFS-based payment channel is another really powerful primitive. It's essentially like the Lightning Network, but built on top of IPFS. And as we heard from other speakers earlier, it's non-consensus because you have content addressing. And then settlement could happen into a number of different ecosystems. So as John mentioned, a particular IPC subnet would make sense to settle against. We could also settle in fiat or any other ecosystem that essentially talks to IPFS. And since most of Web3 has ties into IPFS, we could settle into that.
Thank you.
Do you have docs on that system you guys are building, the IPFS payment channels thing?
It's the future work and research, Hannah.
Oh, sorry. You should check out the Magma team. They've got cool technology. I think independent, so like maybe it doesn't need to be crypto either, so, you know, so you
Amazing.
can look out what they're working on.
Perfect. Thank you.
Yeah.
But also, dogs not everywhere, don't computer. So, there exists something, just not blockchain.
Alex?
When can I start using IPFS?
Amazing. So basically, we did a workshop this week. All this stuff is open source, and generally we have to wrap up the work we did this week. So the team crunched in a good way. We worked together. It's been really amazing, and all of this stuff we'll release with videos and instructions and readmes basically next week. We had it all running this week. Yeah. Thank you.
So yeah, thank you, Boris, for
Thank
the
you.
speech. So final one.
So, last talk of the day, I know, it's late, but I'm going to start off with some questions. Who here has built a dApp or helped build a dApp before? Who here has tried storing some data because of their dApp on a chain before? And who here has stored data that should be private on the chain somehow? So I just talked to someone today at the Wallet Unconf, actually, about this, and essentially they were like, well, we had to store something, but we were at the hackathon and we didn't really know what to choose, and so we just like stick one simple key on it and stuck it on the blockchain. But then, of course, that solution wasn't quite satisfying for them, and yeah, this is what the web native file system is also about. But first, a little bit about me. This is a link to my GitHub. This is how you find me online sometimes. I work at Fission, but I think that's been mentioned a bunch already, so I'm going to skip over that part. Fission, actually, little known, is an acronym. It stands for Fission Internet Software Services for Open Networks. But of course, if you look at this, it doesn't quite spell out. And there are some legal documents, but don't think about it too much. What I want to focus on is the open networks part, because this is what I'm excited about and why this data and storage room is talking about blockchain and data availability sampling sometimes, and these things, and not about AWS S3, right? Because we want to have a permissionless system and a system where you can join and help store data, right? But if it's open, then you have this problem of developers storing data of users and having to encrypt them, right? We kind of want to avoid the situation we had with HTTP and HTTPS, or we kind of are in the same situation where you need to add encryption on top. But how? Like, oh yeah, and encrypt everything, right? But how? So some people would say, well, try TLS from HTTPS, but of course TLS is like point-to-point, you can't really use that. So maybe you take your data cabinet, you zip it into a folder and you age encrypt it. Maybe someone has heard of that. That is something that people do. But you quickly run into problems, right? How do you do editing, right? If your data changes, how do you make that efficient? You don't want to re-encrypt your whole bag of data every time you make a change that is very small. How do you do versioning? Sometimes people want to go back in history. How do you do stuff like forward secrecy, right? You want to share access to parts of your data, but not all of the history of it, maybe. How do you do fine-grained access control like that in general, right? Give access to some parts of your data, but not all of it. If you have a single key for your whole encrypted thing, then, well, you can only give access to all or nothing. And how do you do stuff like concurrent edits, right? If you have things going on at the same time because you've just shared it with a bunch of people and they all make changes, how do you deal with that? All right, with all of these questions in your mind, also us, Fission, was looking at the literature and finding, for example, the Cryptree paper. So this is a paper from 2006 from some people who were storing encrypted data in an open network. And what they did is they built a file system that essentially has a folder tree structure and very intuitive kind of sharing of data where you have a very succinct key that you share and that gives access to a whole subtree of your file system. And like with many papers, there's this one very important figure in it, which basically shows how it works. This is maybe very small for you to see, but in general, this is like a diagram. You see the columns are like different directories. So there's an image directory, holiday directory, Taipei directory, and a metro picture in it. And you can see that here at the bottom, there's a bunch of DKs. They stand for data keys. And in general, all of these boxes and arrows are different kinds of encryption keys that point to each other. Like if one thing points to something else, that means you can reach that in terms of information, or you can like decrypt something with another key, right? So you have all of these data keys. They actually encrypt the folders themselves. And you have these, and I want to point to that specifically, these SKs that are so-called subdirectory keys, which help you just share a single key with which you can like access a whole subtree in your file system. But I want to pull this out because this is the basis of it, and I'm going to ignore all of the other parts of it because this is the thing we took out of the cryptree paper. And we basically did the same thing. We had this kind of hierarchical structure of encryption keys encrypting other keys. And we added more things to it, like, for example, versioning. So if you have multiple revisions, you'll use different keys for each revision so that you can give access to revision 1 without giving access to revision 0. And in this diagram, in general, all of the solid arrows, the orange ones, they are like encrypts the other thing. And these dotted arrows here, they mean this is a hash function from this key to this key. Or in general, you can kind of reach it via a very simple computation. So in this model, you can give access to, let's say, the holiday folder in revision 1 without giving access to the holiday folder in revision 0. So nice, we get versioning. This is not quite what WinFS is doing. It's a little bit more complicated because one other thing we do is we have different access levels in terms of sharing access to history. So you can give access to, let's say, just a single revision and no temporal data. So you won't be able to read future updates to a file or a directory. And then we call the snapshot level. So those are these SKs, these snapshot keys. And we basically borrow the same thing from the slide before for the temporal access level. And now if you look at it, for example, if you just share this small 32-byte temporal key here, and you follow all of the arrows, so you're hashing stuff or you're decrypting things by going to the right or to the bottom, you'll be able to access all of these pieces. But in contrast to that, if you just have access to this small snapshot key here, all you can reach from that is just something within this revision. But even within that case, you sometimes have this issue in this picture that, let's say, I have a file system on my laptop and I want to sync it with my phone for the first time. And what I want to see on my phone is the very latest state of it. But I also want to be able to read back to the very beginning of the history on my phone. So how do I do that? Well, I would have to basically send this key over to my phone, but then have to hash this key for number of revision that I had on my laptop times to get to the latest state, which is very inefficient. And in general, this walking across the history, if you're hashing linearly, is kind of inefficient. So we built something else into the system that we call these skip branches, which are another kind of buffer in this, or layer in the system. And these skip branches have this curious property that you can actually skip a bunch of revisions at the same time and get to the latest state much quicker. And I want to dive a little bit deep into that because that's one of the things that, for example, our CTO, Brooklyn, came up with and wrote a paper, and it's published, so you can read that if you're very interested in. But I also will go a little bit deeper into what's happening there. So what you really need, or what the skip ratchet really is basically, you can think of it as a pseudo-random number generator, right? You need a bunch of random data, which is like all the different keys you're going to use across all of the revisions. And you need it to be deterministic, so that basically you share the state of a skip ratchet so that my phone doesn't have to continually be in contact with my laptop to get the latest keys for the latest revisions of files. It wants to stay up to date. But it also, you likely want it to be backtracking resistant, which means that if my phone has a much newer, or like if I share something with Boris's phone, and his state is a much newer skip ratchet, he won't be able to go back in history. So for random number generators, that generally means if you observe the state of your random number generator at some point, you won't be able to compute some randomness that was prior to that state, which you get by all of the hashing, of course. And the special thing about skip ratchets is you can really efficiently, more than O(n), can skip forwards in time in the random number generator. So again, as with most papers, there is this great figure that basically explains the operations that exist in the skip ratchet. And you can see there's a bunch of states here. Those are the states of the skip ratchet. And at the bottom here, you see the secrets. Those secrets you can think of as the pseudo-random number generator stream, right? Each one of these would essentially be the key to encrypt or decrypt some directory or whatever. And in between, you can see that from state 0, you can just step once, we call this increment, and you get to state 1, and then so on. But there's also these other operations which are called skip and leap. And in this case, this is a simplified picture. Skip skips only 2 steps, or up to 2 steps. Leap up to 4 steps. And all of these operations, skip, leap, and inc, they're all O of 1. So it's not like leap actually takes the time it would take to do all of those incs, it's actually faster. So, how does it work? Well, let's look at the side of it. So let's look at state 0. If you actually use a library and print it out, this is what you see. You see the state of a skip ratchet is some kind of salt, a large, a medium, and a small thing, and some counters. All of these hashes are like 32 bytes. Yeah. And the way I like to think, or the most important part of the skip ratchet is actually the large, medium, and small. They're called the large digit, the small digit, and the medium digit. And the reason they're called digits is because it's very similar to just counting. The idea is basically when you count, you do the thing, right? I don't need to explain it to you. And at some point, you'll have a carryover, and you reset the small digit, and you count the next digit, right? And you take this idea that you didn't really have to count through all of the small digits to get to 10 and use it for the skip ratchet. So the way you count in skip ratchets is you have the small digit and you hash it and you get the next state. And then so on and so on, right? And we also track that in the counter. And then at some point when your counter is 255, so unlike the base 10 thing before, this is base 256. When you need to carry over, what you do is you hash the medium digit and reset the small digit, not to the value at the very beginning, but to a value that is derived from the previous medium value. And so that is just a hash of the salt together with the medium value before. And if you look at this, the value of the small digit does not depend on any past value of the small digit before. So that means at any time, you can just skip to the next, we call the medium epoch. And yeah, so you arrive to this state. And if you want to skip to the next large digit, you again just hash the large digit, the medium digit then gets reset, and also skip forward once, and the small digit gets reset essentially twice. And if you look at all of this, nothing here depends on the medium or the small values from the history of the skip ratchet before. Which means you just skipped 65,000 or more of that steps, and you didn't have to do all of the hashing work one by one. So yay, this actually exists. There's an implementation of it if you care to see, and if you want to try it out, basically get all of that. So with that, with all of this key hierarchy, with all of those skip ratchets, we get efficient history, versioning, and fine-grained access control. We have access control on individual files and individual directories. We get temporal access. We get snapshot access. But there's this thing in encryption where we often use the key, the symmetric key to encrypt stuff, to also verify the integrity of what we wrote. So if you look at something that is encrypted, of course, you don't know if that is just valid or not, putting valid in quotation marks. And what we do is we add the authentication tag to verify that. But the authentication tag basically means someone produced the ciphertext who also knew the the symmetric key to encrypt it. And that can be verified, but it ties the symmetric key that gives read access to write access. And sometimes you don't want these two things to be the same thing, right? Sometimes you want to give someone read access, but not write access. So there's another system you need to build on top to really separate them. And often that is something that is public key cryptography or public key infrastructure based. So you have some public key that is the owner of the file system, and you can give out access to individual subparts of your file system by signing things and saying this person has access to this subpart of the file system, right? So how does this work? Well, if we look at a file system in WinFS, so this is just some kind of file hierarchy. There's a bunch of things with different names, and you encrypt them one by one. You lose all of the connections between them because you can't read them anymore in the encrypted form. But crucially, I want to point out, we take all of these things, put them in a big hash map, and now we need to name them somehow, right? So in this system, you would basically namespace all of the names, and in this system, you would basically do, okay, well, if I give someone access to, let's say, the work directory, I would sign something that says that and put it in the hash map, and then every time someone provides an update, they would say, okay, well, I got the signature that I have access to the right work directory, right? But of course, this is not really privacy preserving. You're really leaking a lot of information about the private and the work directory publicly in your open data network, so that will suck. So what you do is, well, step one, you replace all of the identifiers with just random numbers. We call them I numbers. Again, 32 bits. This is just smaller for convenience on the slides. But still, you're leaking the relationship between files and directories. Like what is a subdirectory of what, or which files are entries of what other files. And so in that case, you can still analyze the structures of your file system to, for example, see if someone is using a certain kind of app that always has a certain kind of file hierarchy structure, right? So what we do is we actually just hash these things. We also hash them together with a revision that is derived from the skip ratchet, and take all of these things, put them into a hash map, and I'm just gonna go through this very quickly. At the end of the day, this is an IPLD hand. You've heard the words before. You get a root hash. We're happy. But what we've lost, of course, is publicly verifying that these things are actually subdirectories or entries of something else, right? So, some magic going on in this hashing function, actually. Because it's just not a normal SHA-3 or whatever hashing function. What we use is an RSA accumulator. So, again, this is from the literature. It's an old thing. One-way accumulators is the paper where they introduced it. And then there's also the batching techniques for accumulators paper, where we basically get a little bit of more privacy protocols or proofs, more privacy preserving proofs for accumulators, and a bunch of batching goodness that makes them faster. And the way it basically works is you need some RSA modulus, and the hashing function is in practice like taking the some quadratic residue, which you call the generator G, and taking that to the power of all of the things that you are hashing. And what that gives you, like all of these I numbers again, these two 56-bit numbers. And you're taking modulus of your RSA modulus. And what you get with all of this is there is a with those papers before, there's a proof you can do that basically some parts of this, let's say the hash of I number 1 and I number 2 are part of the accumulator that came out at the end. And this is exactly what we need. Because what you're, now that all of our identifiers here in the hash map, now that they are all RSA accumulators, you can basically prove that, well, these two directory names were part of the path, where the path is represented by the final accumulator. So you can kind of construct this proof, and you can also even prove at the same time that it's like part of multiple things, which is kind of neat with the batching techniques paper. I don't have all of the time in the day, so I can't go into all the details of this. But yeah, basically we are using the PokeStar and the KCR algorithms from the paper. So look into that if you're interested, or talk to me. All right, so what would basically happen when you give out write access now, just to wrap this up, is you sign the path that you want to give access to in the form of an accumulator. And when you verify write access, and you give it to some person, and when you verify write access, what you do is, well, you see the diff between the two versions in the file system in the form of the hash map. And you go through all of the keys that changed, look at the identifiers, and make sure that there exist proofs, or that the proof that is provided basically covers all of these keys. And finally, you just verify also the signature, of course. All right, what you get is actually pretty neat, because we now have read-write access separation. We can actually verify writes without having read access. So think of, let's say, putting WinFS on a blockchain, or think of putting WinFS into some hub that relays and broadcasts the latest state of it. It can actually, when it ingests the data from new clients, verify that the writes were correct before they were actually broadcast to all of those clients, before my phone is forced to also verify this again, right? So you're saving a lot of compute there, and you're making the whole system a little bit more resistant to abuse in that regard. Which is kind of hard if you have an encrypted system, right? You're always forced to do all of the computation of the clients that actually decrypt, usually. Yeah. And yeah, you still have this normal system where if you have access to a certain directory, you inherit the access for all of the entries within it. So there's one last thing that I didn't touch upon, which we need to talk about, and that is concurrent writes. If I'm on a plane and I'm doing stuff on my phone, and someone else is also working in my WinFS, we may end up doing concurrent writes. And that's a thing we want to be able to deal with, right? And you may have noticed that in when using Dropbox or any similar kind of service, or Git for that matter, I guess. So yeah, how do you do that? Well, in WinFS, we actually keep a lot of the history, which is really good, because that allows us at the end to look at what happened and reconcile changes. That is one thing, but the other thing is we're also encrypting everything. So the thing that the hub sees, if let's say we're doing all of the merging at the hub, is just this kind of hash map of encrypted data. So what does it do when someone else comes to it and actually does a valid write, but it writes to the same key, but something different? Well, the hub can't do anything. So when it merges these two things, it just stores both versions. This is one of these cases where we can't do better, unlike with RSA accumulators sometimes, than just pushing off the computation to the clients that will later have to do it when they read, right? So you resolve conflicts at read time. Now, what does it look like? Well, the resolving algorithm is actually fairly simple. If you read a revision, which turns out to have like multiple conflicting writes, if those two are, let's say in this example, two directories, and then they, let's say, have two different things that were written into them. So one version added a file or a directory work, and the other revision added a directory life. You just merge them together and you keep work and life, both directories. But if you have a change in the same key, you need to recurse. You look at the changes inside, and if you realize, oh, well, these changes are reconcilable, well, then you merge them together, you create a new revision, you write a merge directory to it, and you recurse back to the top, and you link back in history. That's neat if you actually have, let's say, a file where there's a conflict. then we can't do anything better than just tie break, what people usually call it, and you use the biggest hash, smallest hash, something like that. But and so you're kind of losing data, but you're also very consistent. So you have a consistent state across all of your devices, let's say, which is important. And the other thing you get is because you're writing and persisting the history, later if you want to look at it and fix all of the things that were replaced or deleted, you can do that. Or even have apps that, let's say, write a JSON file as their app state. And this JSON file actually has a particular structure. Let's say it's a CRDT because it's an app that knows how to do that or structures the state that way. The app can go back into history, look at different states of it, and just merge them together and write a new revision if it wants to. But in principle, we need some way of like producing a canonical latent state. So we tie break on hash in those cases. But yeah, so that's basically the rough structure of a merge algorithm in WinFS. And yeah, where are we at in terms of implementation? What does exist and what doesn't? Well, there's an implementation in Rust, RS-WinFS. It exists today. You can use it, and I encourage you to do so. There's some docs, there's some GitHub link, whatever. It is very portable. So essentially, the Rust crate is just a bag of pure functions, and you add some, like there's an interface for a block store. You just provide essentially the networking and the storage layer via the block store, or on that, roughly hand waving here. You serialize, deserialize some keys, provide some asymmetric encryption and decryption functionality, and that's all you need. And that's all external to RS-WinFS. So this gives it a lot of portability. And for example, so it's very binding friendly. So for example, it was compiled into, let's say, people who were using it in Swift, people who were using it on Android, from Java, or just using it in the browser via Wasm, which was one of the main things we were building it for at Fission. So it's a community project. So there's people, for example, FunctionLand has built FX Photos, which basically takes a bunch of photos and is an Android app and iOS app where you can upload your photos and it gets stored in WinFS, encrypted and then put into a chain. There's Banyan, we've heard about them before. They use WinFS to encrypt data and put it onto Filecoin. And they've actually contributed a bunch of things to WinFS, so awesome shout out to them. Just recently, there has been a project, Capiloon, that has been integrating with WinFS, which is basically a mobile operating system that is building on WinFS. So the operating system underneath actually uses WinFS, and you can share data across devices, between people, that kind of thing. It's the most recent thing of them all. And yeah, with that, use it, talk to us, get involved, and thank you.
So yeah, then I guess thank you for all the speakers coming today. It's been a good afternoon, and everyone is giving quality talks today, and I hope everyone enjoyed the time here today. So thank you, speakers, again and also thank you for all the attendees right here to attend our Fenbushi Research House event. So yeah, thank you.